What is cosmology? Cosmology is the attempt to answer some of the greatest questions that have ever posed to humanity. How did the universe begin? What is the universe? Why are we here? What makes up the universe? When will it all end? What's it made out of? What's the eventual fate of the universe? Is there a meaning? And most importantly of all of that, how can we learn anything about any of these questions? Cosmology seeks to answer these questions using experimental science and measurement to understand the origin and fate of the universe. We attempt to make models of the universe in various ways and see which ones work, which ones fit observations, and then make observations that either to test those ideas. And if the ideas don't fit the observations, then we have to discard the ideas. And if the observations are challenging and new, then we have to understand them with new ideas. The universe itself is very vast. It is composed of things like people and oceans and planets and stars and galaxies. And it is composed of normal matter, dark energy, and we think of the things that go from the very smallest to the very largest. And we look at the cosmic microwave background, we look at the origin of things from the Big Bang nucleosynthesis. We look at our place in the universe, how it has changed from being thought from ancient times when we thought we were at the center to now we know we are one of a multitude of galaxies in a vast cosmos. With that very brief introduction to the concept of cosmology, I'd like to welcome you. My name is Jason Kendall. I have taught cosmology at William Paterson University. I have also done quite a bit of things, as you probably have seen on my YouTube channel, for introductory astronomy. And so I figured I'd put my cosmology course on my YouTube channel. If you wish to follow along, you can certainly do so. I am utilizing as my basis Dr. Barbara Ryden's textbook, Introduction to Cosmology. She's a professor at Ohio State University, and I've used her textbook in my course at William Paterson University in the past. So why am I doing this? Principally because cosmology is really enjoyable to me. It's what I have my master's degree in, and I find it a fascinating subject. So what should you expect? We're going to go through this textbook, and I'm going to hit every single chapter and every single section in it. I'm going to derive mathematical equations and give you the theoretical and observational understanding for what cosmology is and where and what we can understand from it. In order to understand anything about the cosmos, we have to understand how to measure it. Because in any science, no matter what it is, you have to be able to measure things. You have to have reliable ways of measuring those things, and you have to agree on what you're going to measure on. So part of the agreement of understanding measurement is the units that we use to measure things by. And the standard thing that we're going to talk about, some basic units to begin with as this introduction. We will introduce to the idea of distance. We know about meters. Meters are about 1 meter long. Most of the world knows what a meter is, but in the United States, we like to think of yards and not meters. But we're going to stick with meters. And the meter is a standard sort of human-sized distance, and the kilometer is a standard human-sized distance. But the real astronomical distances start when we look at the astronomical unit, or the average distance between the Earth and the Sun. That is 1.5 times 10 to the 8th kilometers, or 150 million kilometers. The next most interesting thing from the astronomical unit for unit of distance is the light year. And that's mostly a kind of a cultural thing. It is the distance that light will travel in a year, which is about 10 to the 13th kilometers. More important than the light year is the parsec. The parsec is a geometrically derived observational distance to something that's very far away. A parsec stands for a parallax of 1 arc second. So what's that mean? Parallax is that apparent shift that you see in something when you say, hold your thumb. Let's say that something is your thumb, and you hold it at arm's length, and you blink your eyes left and right, and your thumb appears to shift in position with respect to background things. Now, that shift might be big, might be a degree or so, and the distance between your two observation points, your eyes, is only a few inches. Let's say now the observation points are now separated by 1 astronomical unit, and the angular shift of your thumb is now 1 arc second and not a degree or 2 or 5, or not even a half a degree, not even a tenth of a degree, but 1/3600th of a degree. And that means that it's going to be very far away because that shift will be very small, and the baseline is very large. So you're going to have to be really far away such that a really large baseline, 1 astronomical unit, will give you a very small shift. And that ends up being about 3¼ light years, or 206,264 astronomical units. That's the distance. But this is a geometric distance, and so there it's a direct observational. And therefore, it's really important and better than light year because uh, photons don't have clocks attached to them, so a light year is really kind of meaningless. So this is the main geometric measurable distance to the stars. And the typical distance between stars is about a parsec or so. But when we think of the largest collections of stars, like the Milky Way or galaxies, we have to start measuring the distances to galaxies in terms of megaparsecs, 10 to the 6 parsecs. And then when we think of distances or size scales of galaxy clusters or distances between clusters, we start thinking in terms of gigaparsecs or billions of parsecs. For some basic ideas, the distance to the nearest star is about 1⅓ parsecs. The distance to M31, the Andromeda galaxy, is about 3/4 of a megaparsec. And the Virgo cluster of galaxies is about 16 or 17 megaparsecs. The size of the observable universe, the size from if we look one direction and turn our heads 180 degrees and look the other direction, that is the observable universe. And that goes in any direction with which we look one way than the other. And the diameter of that is approximately 28 or 29 gigaparsecs. So these units of distance are very large. The next unit we'll talk about is the amount of stuff there is in a place, and that stuff we will call mass, and mass has a very interesting set of properties. But we will first say that we'll kind of agree that we understand what mass is and that it is some accumulation of stuff. And the standard unit in the SI units is the kilogram. And kilograms are pretty important, but for astronomical and cosmological purposes, they are not. More importantly, we use the solar mass, or the mass of the sun, which is about 2 × 10⁻30 kilograms, which is a lot. And the mass of our Milky Way galaxy is about 1 trillion solar masses. And the mass of the Virgo cluster of galaxies is approximately 10 to the 15th solar masses. The solar mass is a very good unit, but we can see that galaxy masses can be somewhere between a billion, or very tiny galaxies on 1 million or so solar masses, up to trillions of solar masses for the very largest of them. So our unit is going to be the solar mass for our base unit of measurement. Just as important as mass and distance is time. Time is really important for physics because it doesn't matter if there's a thing over there that has mass and it's over there at that distance. We want to know how things work. And so things work means that there must be some time that's involved. And in the units of time that we know are, of course, seconds, which are like the second minute of an hour, which is a very interesting way of thinking about it historically. And finally, we will continue with the idea of the second as in the Earth year, the time it takes the Earth to go around the sun, which is about 31.5 million seconds, or pi times 10 to the 7th seconds, which is really close to pi times 10 to the 7th seconds, which is fascinating. Anyway, but cosmologically, that's not very important. The second, even the year isn't important. Cosmologically, we more think of things in millions of years, like mega years, 10 to the 6th years, or giga years, 10 to the 9th years. The age of the Earth is about 4.567 giga years. The age of the Milky Way is approximately 13.5 giga years. And a characteristic age for the universe, which we call the Hubble time, is about 14.7 gigayears. And these are the types of time units that we care about cosmologically. We really do care about millions of years and billions of years in cosmology. Now, once you take some stuff that has mass and it's over there and it is moved from there to here, it takes energy and work to move things from here to there. And so we have to then define also the units of energy and power. The standard SI unit is the joule, and or we can also call it a Newton meter. And the units on the units of energy are different because they're made up of mass and distance and time. The unit of energy is a kilogram times a meter squared over a second squared, or a Newton meter, which is a unit of force, which is a kilogram meter per second squared, exerted through a meter. That is the unit of the Newton meter, or joules in terms of the base units of mass, time, and distance. So the watt is 1 joule per second, which is another SI unit. And next we have the good astronomical unit of the solar luminosity, or how much energy the sun is putting out every second. That's about 4 times 10 to the 26th watts, which radically dwarfs the entire output of humanity, which is on the order of some numbers of hundreds or thousands of terawatts, which is only 10 to the 12th. So the sun puts out a lot more energy than humanity ever will. The luminosity of the Milky Way can then be measured in solar luminosities at about 3 times 10 to the 10th solar luminosities. And you can have extraordinarily bright objects that can be seen from extreme distances like quasars. And specifically, an example quasar is 3C273, which has about 4 times 10 to the 12th solar luminosities. And all of that energy is being created by a supermassive black hole at the center of a distant, distant galaxy. And we will be using energy and power often in the quest of cosmology and astronomy. In addition to these extraordinarily large units of distance, time, and energy and mass, we also are concerned with the very small, because the universe, as we will find, was started in a very hot, very dense, very small place. Well, not really place, but state, rather. And so we have to understand the units for the very small. And the joule is sometimes too clunky for that. And we would rather use a unit from, say, particle physics, because we're going to be talking a lot about particles and how individual electrons and protons, or huge masses of them, contribute to the cosmos. So a useful unit on particle physics size scales is the electron volt, which is the amount of energy that an electron gets when it is accelerated through a potential of 1 volt. And it's a very, very, very tiny, tiny energy. It's 10 to the minus 19th joules. It's a tiny energy. The electron volt's a very useful thing. It's used in particle physics, and you'll use it in laboratory experiments and in undergraduate physics labs too. Importantly, we just remember that the rest energy, which is the E equals mc squared from Einstein, the rest energy for an electron is about half of a mega electron volt. And the rest of the proton rest energy, meaning how much energy it has simply by existing, that's what rest energy is just under 1,000 mega electron volts, or almost a giga electron volt. Now, a neutron is almost the same thing as a proton, but just a little bit bigger. The neutron's rest energy is a touch bigger because it is neutral. And so in order to make a neutron, an electron and proton have to be combined in the presence of a neutrino. But the energies, the rest energies of these particles, is on the order of a giga electron volt, or 1,000 mega electron volts. Now, the size of a hydrogen atom is very small, so those are their energies, but their rest energies, the energy for existing. The size of a hydrogen atom is about an angstrom, which is about 10 to the minus 10th meters. So we talked about meters, we talked about light years and parsecs and gigaparsecs, but we also care about the size of a hydrogen atom, which is 10 to the minus 10th meters, and the size of a proton, which is extraordinarily small at about 2 femtometers, which is 10 to the minus 15th meters. So that's a 0 with 15 with a dot, then 15 zeros, and then a 2 after that. That's the size of a proton. And so you'd have to stack 10 to the 15th protons up in a row just to get 1 meter. Or if you think about it, to get 10 to the 13th in order to get 1 centimeter. So that tells you roughly how many protons there could be. across your thumb if they were stacked that densely. They aren't stacked that densely, but in some astrophysical cases they are. But the very small are also incredibly important for cosmology because these small environments arise when we talk about Big Bang nucleosynthesis. Just as important as these base units are what exactly we're measuring. And we have found over the course of hundreds of years of exploration and discovery and scientific advancements that there are some fundamental constants in the cosmos that stay put. The speed of light in a vacuum, which is 300,000 meters per second, or 300 million meters per second, or 300,000 kilometers per second. Newton's gravitational constant has that value of 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. And that's an interesting thing because the equivalent units are like meters cubed per second squared per kilogram. It's interesting that you have a meters per second as a fundamental constant and something that has meters on the top and seconds on the bottom and kilograms on the bottom as the equivalent units. Newton's gravitational constant obviously is the thing that relates the force of gravity, force due to gravity, as discovered and elucidated by Newton when he said the force between two masses is proportional to their masses and inversely proportional to their distances, and that proportionality constant is this g. Likewise, the speed of light in a vacuum has been well understood for a long time, but the ancients thought it was instantaneous, and one can easily forgive them for thinking so because of the high speed of that. The reduced Planck's constant is simply Planck's constant divided by 2 pi, because frequently that 2 pi is part of angular momentum in quantum mechanics. So Planck's constant is basically a way of saying how much energy is in a particular particle. It was needed as a proportionality constant to Planck's law for blackbody radiation. And it is one of the more critical things that is in physics because it also is the proportionality constant for the energy of a photon. It also comes into play when we talk about the energy of quantum states of particles. So Planck's constant will be incredibly important later on, but notice that number is extraordinarily small, 10 to the minus fourth joules seconds, or 6 times 10 to the minus 16th electron volts seconds. So it's kind of a weird unit. It's not electron volts per second or joules per second. It's joules times seconds, which is an odd concept. Well, we'll get more to that later. Boltzmann's constant is also incredibly important as one of the fundamental constants of the cosmos. It is a bridge between heat and statistical mechanics for us to understand energy flow as a product of heat. Now, all of these things, the numbers of these are based off of these SI units of meters and seconds and kilograms and kelvins. And these are all very earthbound things. And they're all units that we're comfortable working with. But they're all based on what humans would measure them to be. And that's not necessarily what everybody in the cosmos would measure them to be. Now, if we wanted to measure them kind of what everyone in the cosmos might measure them to be, we might try to find some fundamental units that aren't so based off of whether or not we orbit the sun and that we're about a meter tall and that we use base 10 as our primary way of thinking, and that we don't think of in terms of seconds and we don't think in terms of kilograms. But let's see if we can figure out these units, maybe called Planck units, which are based off of the idea that you can combine these fundamental constants together to get things that are fundamental to the way of the world in a certain way, or the way of the cosmos. So a Planck length would correspond to, which is 10 to the minus 35th meters. And you could see that it is the square root of the product of the reduced Planck constants times the gravitational constant divided by the speed of light cubed. Now, why would we do this? Well, the Planck length is considered to be a length that where the gravitational influence is roughly balanced by quantum mechanical influences. And so This might be a length upon which we might say, oh, if gravity and quantum mechanics are to be reconciled as competing theories of how the universe works, they work in their own regimes, but they don't necessarily mesh very well. The Planck length might be a good place to look for where they meet. Similarly with the Planck time, which is similar to the Planck length, except you divide by another speed of light squared under the radical. And that's a very short time frame, which is about 5 times 10 to the minus 44th second. So the Planck time might be in a unit of time whereby you can't necessarily tell the difference between a gravitational interaction and a quantum mechanical interaction. That might be one way of thinking about it. The Planck mass is about 10 to the minus 8th kilograms. The Planck energy would be, of course, then the Planck mass times the speed of light squared. And that's an enormous value, about 2 times 10 to the ninth joules, or a huge amount of electron volts, as you can see. The Planck energy is, of course, very large compared to the proton rest mass. So we don't really expect a proton rest mass to be anything related to a Planck mass. Now, the Planck temperature is also interesting, meaning we take Boltzmann's constant and we take the energy and we convert that energy into a temperature. And that gives us a really fascinating statement about saying how heat is transferred on quantum mechanical scales when the density of material is indistinguishable between gravitational influences and quantum mechanical influences. Planck temperature is expected when it would be the temperature expected when something is all compacted down into a Planck length, or a Planck mass is compacted down to a Planck length. Maybe that's a good way of thinking about it. But the Planck temperature is a unique thing that can be devised from these fundamental constants. Mostly what these Planck units allow us to do is they allow us to treat these fundamental constants truly as conversion factors. So if the speed of light is 300 million meters per second, then 1 second equals 300 million meters. Likewise, then we can say for all of our equations in Planck units that c is equal to 1. It's just 1. And that likewise, we can say if we're working in Planck units, then Newton's gravitational constant is equal to 1. And the Boltzmann constant, K, is equal to 1. Now the Planck constant, the reduced Planck constant, is also set equal to 1 in these units, in Planck units. We then say that everything's a length. 1 second equals 300 million meters. 1 kilogram equals 7 times 10 to the minus 28th meters. And 1 Kelvin is equal to about 10 to the minus 67th meters in these units, which is a very weird way of thinking. But now using the idea that everything's a length and setting all these values equal to 1, we can understand that there's some non-human-centric ways of thinking about units. Now, funny enough, Planck's constant works out to be 10 to the minus 70th meters squared. So it's an area rather than a length, but we can still set it equal to 1 and use it in these length units. All of these things are done such that you can simplify equations. But if you then say, wow, Einstein's great equation, E equals mc squared, now becomes E equals m in these units. That just sounds and looks weird, but it tells us something also, that mass and energy truly are the same thing, and the conversion factor between them is simply this unit conversion between seconds and meters. So we can think of these conversion factors as helping us understand that we can geometrize almost everything in the universe down to a length. And that's helpful in the equations. But for the sake of clarity for the rest of this course, I'm always going to include the C's and G's and H's and Boltzmann constants and so forth. I won't remove them. You will see that in many graduate level textbooks and treatments, but I think that's pretty confusing. So I'm going to let you understand that we can use these as conversion factors, and they're somehow converting things between space and time and mass and heat. And let that be as a kind of a philosophical way of thinking. But it's also extremely useful mathematically and also helps us what would be fundamental in measurement across the universe, irrespective of the nature and source of the observer. With all this in mind, let's go over the briefest possible history of cosmology. Cosmology has been with us since the dawn of human civilization. Earliest peoples pre-civilization times must have looked up at the night sky and seen the stars and wondered if they were campfires like their own. And they started to tell stories, and those stories made up constellations, and we made stories about the patterns in the sky. Eventually, when civilizations arose, such as ancient Egypt, the goddess Nut was was the goddess of the sky, and she overarched the earth. Her brother Geb is the earth, but at night her body was said to shimmer with the stars, and during the day the sun god Ra raced across her to traverse from her feet to her head every day, and then repeated it. What the sky was, what she was overarching, how she went through that wasn't important. The explanation was the gods were making sure of that. We've left these gods behind now, and we see how this progresses. These early stories come from 2000 BC, almost 4,000 years ago today. But 1,500, 1,600 years after these ideas were first conjured by the Egyptians, the ancient Greeks, in the form of Aristotle, came up with other ideas about cosmology. Aristotle believed that the Earth was at the center of the cosmos and was unmoving and fixed, and had a real problem with parallax because he said that if there's some parallax, we should see them moving in the sky as you go from one place to another. But he was understanding that the Earth was round and that the Earth was in the center of many celestial spheres upon which the planets rode, and the sky was one of them. Contemporaneously to Aristotle was Aristarchus of Samos at roughly around 300 BC. He developed a heliocentric model 400 years before Ptolemy created his geocentric model. And Aristarchus's model said that the sun was the center of the solar system, and because it seemed to be the largest object. And in fact, he was able to make rough calculations using eclipses to the relative sizes of the sun, moon, and Earth, and found that they were and their relative distances too. So the sun was deemed by him to be very, very large. And so therefore he philosophically put it at the center, not because of any scientific idea, but because fire is nobler than Earth. However, Aristotle's idea won over Aristarchus's ideas because of parallax. If the Earth were moving, then we should see parallax in the stars, which we do not see, which Aristotle and the Greeks couldn't see. But that stuck around for a long time. The demonstration of the size of the Earth came with Eratosthenes, who roughly around 200 BC described a process by which he could measure the shadows of a stick standing straight up at noon at the solstice or particular times of day, or the lack of shadows down the hole of a well. And so the difference between two locations on the Earth, one at the equator and one about 7 degrees below the equator, was enough to give him an estimate for the circumference of the Earth given the distance between these two cities. And that proved that the Earth was round and was a sphere back in 200 BC. Roughly about 150 AD or so, the middle of the 2nd century, Claudius Ptolemaeus created an Earth-centered cosmology where the Earth was at the center of the universe, and every one of the planets in the sky, the wandering stars, the planetas, these wandering stars were each fixed to a celestial sphere that rotated around the Earth, the sun included, the moon included too, and the stars were on their own celestial sphere. This idea, this cosmological idea, lasted for nearly 1,500 years. 1,300 years later, Nicholas Copernicus came up with the idea of a sun-centered cosmology, where the sun was at the center and the Earth went around the sun. Now, he didn't do this because of any scientific idea. No, he felt like it was more aesthetically pleasing. In fact, all of the problems that Ptolemy had with his ideas around the center, the Earth, the sun-centered universe, where he had to put epicycles upon epicycles and equants and deferents. They were also present in Copernicus's idea, because Copernicus, like Ptolemy, believed that all of the heavens had to be in perfect circles, and these perfect circles were a requirement of the heavens, because they still stuck with Aristotle's idea that the earth was corrupt and the heavens were perfect. So this idea still existed. One of the greatest proponents of Copernicanism was, of course, Galileo Galilei. In 1609, published a paper that predominantly tried to push the Copernican system. He looked through a telescope in 1609 and saw that the sun had sunspots. The moon was not perfect. There were more stars than could be seen with the naked eye, and that Jupiter had its own set of moons or stars that went around it. He called the stars going around Jupiter the Medicean satellites, because he was trying to get money from the family Medici, and it worked. His idea, though, was based on Copernicanism, and that Copernicanism was not really the real thing. Contemporaneously to Galileo was Johannes Kepler. In 1609, he published his ideas about the orbits of planets. He was trying to understand, as he said, the mind of God and how things worked. And so when Tycho Brahe died in 1601, Kepler obtained Tycho's amazing observations of the location of Mars in the sky and determined that planetary orbits were ellipses, which are different than Copernicus saying all planetary orbits are circles. And planetary orbits being ellipses, where the sun is not the center of the ellipse, but one focus of an ellipse, which is different than the sun being the center of all the orbits, such as Copernicus said. And Copernicus also said that the speed of every planet in the orbit is constant, but Kepler found that the speed varies as the planet goes around. And the orbital period of the planet around the sun is related to its average distance through the relationship that he found, which was the orbital period squared is the same as the average distance cubed. Now, the orbital period has to be measured in Earth years, and the average distance has to be measured in astronomical units, or the average distance between the Earth and the sun. Now, he did send this in 1609, sent his copy of his book Astronomia Novia in 1609 to Galileo, who completely dismissed it, thinking that it was really hard to read. And later in his life, Kepler said, yeah, this is too hard to read. I can't even read it. We'll go now forward to the latter part of the 17th century and the early part of the 18th century with Sir Isaac Newton, who showed that the laws of motion of the heavens are exactly the same as those on Earth. He developed his law of inertia, the law of force, the equal and opposite law, and of course his law of gravitation, that showed how Kepler's laws can be derived from first principles. Newton's law of gravitation became an incredibly important element in understanding how things moved. His F equals gmm over r squared equation that showed how forces worked allowed for the understanding of planetary orbits. Now, it's really interesting to think, if you look at Galileo's book on the description of two world orders, he got very close to the concept of an infinitesimal, which Isaac Newton used in his calculus in order to solve the concepts of gravity. However, it took until 1729 when James Bradley finally published his observations of Gamma Draconis, where he was trying to see stellar parallax. He found something else. He found stellar aberration, and that is the thing that showed that the Earth was moving through space. And finally, a proof, in the 1729, over 2,000 years after it was proposed by, a sun-centered idea was proposed by Aristarchus of Samos. Now that Aristotle's ideas had been put to sleep by that observation in 1729, 61 Cygni was observed to have the first measured parallax by Sir William Bessel in 1838. This parallax was approximately a third of an arcsecond, and that's about 11,000 times smaller than a degree. And he found that the first star where its distance was known through parallax of about 11 light years or 3.5 parsecs was seen in 1838. Now that Aristotle's parallax had been taken care of with Bessel's observation of 61 Cygni, which is understandable why Aristotle would not have said it. It's such a tiny effect that it is not possible to see with the naked eye. And finally, understanding that the Earth was actually moving and giving Galileo finally some rest in his grave, Foucault's pendulum in 1851 showed that the Earth was rotating because if the Earth is a sphere and rotating, then it's a rotating reference frame. And if it's a rotating reference frame, it'll exert a Coriolis force on a pendulum. And that's what is seen. The pendulum itself precesses due to the Coriolis force. The period of the precession depends upon the latitude at which you are on the Earth. So if you're at the North Pole, it'll be a 24-hour precession. And the closer you get to the equator, the longer and longer and longer that'll be. And that's all due to the fact that we're in a rotating reference frame. In 1917, Albert Einstein developed his theory of general relativity, which allowed for the understanding of the combination of space and time and mass, and showing that space-time and mass interlock and interlink, meaning mass tells space-time how to curve, and space-time curvature tells mass how to move. And that is a fundamental idea inside of general relativity. Contemporaneously to Einstein's work, Vasto Slipher at Lowell Observatory between 1914 and 1922 were measuring he was measuring the radial velocities of bright nearby spiral nebulae or galaxies. And he found that they had a systematic redshift, but he did not think that they were anything cosmological. He was just making good measurements. In 1929, Edwin Hubble was able to get distances to many of the galaxies that Slipher had gotten for redshifts, and he got redshifts of his own for many of the same galaxies. And he found a relationship between the redshift of a galaxy and its distance, and he was using Cepheid variables in order to find those distances. Therefore, finally had an idea that the universe seemed to be expanding. And this was the first observational evidence, and it's been supported time after time after this time. Next, because of the war effort in the Second World War and the work on nuclear bombs, Big Bang nucleosynthesis was something that was researched by many of the same people working on the Manhattan Project. Ralph Alpher in 1948 published a paper that showed that if the universe could be thought of as running backwards in time from Hubble's expansion that was discovered and go to a smaller and smaller state, it would be hotter and hotter and eventually should be hot enough to form elements and do nucleosynthesis. And so that is the birth of the concept of the Big Bang. As a result of Alpher's paper in 1948, it was understood, or at least put into the literature, that there should be a background radiation that exists throughout the cosmos as a result of this cosmic nucleosynthesis, and it should be in the radio frequencies today. It was forgotten for a very long time period, but this prediction was incredibly important. In 1964, Penzias and Wilson discovered the cosmic microwave background that had been predicted by Alpher and Gamow in 1948. Their discovery came about as a side product of some radio research they were doing for Bell Labs in Holmdel, New Jersey. They accidentally discovered a background hiss in their radio receiver they couldn't understand and couldn't remove from known sources. The observation of the cosmic microwave background was first put into incredibly strong footing in 1992 by the COBE satellite that was launched by NASA. And it showed that the cosmic microwave background is a perfect black body at a temperature of 2.725 Kelvin. And it was one of the most perfect blackbodies ever seen. And I was actually at that conference in 1992 when this was announced. It was an enormous standing ovation with everybody in attendance at the American Astronomical Society. The Hubble Space Telescope was in the sky, and one of its major things that it was going to do was to try to discover the rate of expansion of the universe, and teams led by Perlmutter, Schmidt, and Reese were looking for the expansion rate of the universe, and at the time, people thought that it was going to decelerate. And so people were looking for the deceleration of the universe. And in 1998, the cosmological community and the universe was astonished when it was discovered that the universe was not decelerating, but rather accelerating. And this was the first time we understood that the universe was suffused by dark energy, which took up most of the universe, at least three quarters. In 2013, on the heels of NASA's Wilkinson Microwave Anisotropy Probe, ESA's Planck mission released its results and determined the age of the universe is 13.799 billion years old. And the accuracy to which they determined the universe's age was better than we know any of the fossils in any museum. It also determined that dark energy made up about 68% of the cosmos, and dark matter composed about 27%, with normal matter making roughly about 5% of all of the universe. With all of this information and the materials that are coming out of the James Webb Space Telescope, we're in a golden age of observational cosmology. Cosmology has left the realm of stories around campfires told by people or religions and has become a precision science that has hypotheses and observations and tests and experiments that can actually determine the nature and age of the cosmos. This entire course will cover all of the aspects of cosmology, from the theoretical side to the observational side, to the observational tests, to general relativity, to all of these things. And we'll look at many of the new results that are happening as a result of the latest observations from the James Webb Space Telescope. I'd like to take a moment here and thank all my Patreon supporters. Without their support, it's really hard to keep going and doing this. But it's just as important for you to subscribe to this channel and like the videos that you see and share them around. There will be a lot more videos because the textbook is long. So I hope you'll stick with me through this fantastic course as we learn cosmology together. See you soon. Hey there, everyone. Welcome back to this Introductory Cosmology course. We're on Chapter 2, and we're talking about fundamental observations, and we're going to be talking about this Olbers Paradox. The night sky is actually dark. If you're just tuning in, this is your first time in my cosmology course, please make sure to watch all the videos in the series in the order that's in the playlist shown below. And that way you can get the entire experience and get everything in the correct order, because this is a college course following a textbook. So also, please subscribe to the channel so you'll be notified when the next video in the series is released. And with that out of the way, let's get to it. Since we wish to understand the cosmos using science, we need to observe it and try to understand our observations using known physical principles. And as we make our understanding, it's critical that we discard ideas that cannot be supported by observations. We also have to follow known physical laws, and any models that we describe must have observationally verifiable consequences. Otherwise, it's metaphysics, or worse, just useless blather. So we'll need to start to understand the fundamental observations. There are 4 that we're going to cover in this chapter 2, and the first one is the night sky is dark, Olbers Paradox. And that's kind of a funny thing to say. It is actually odd that the night sky is dark, Because logically, according to many theological ideas and, quote, common sense, it should be filled with stars. The night sky is dark. Obvious astronomer is obvious, obviously. Or is it? Go outside at any time when it's truly dark, no clouds, away from city lights. You see mostly dark sky, optically, punctuated with a few thousand stars. That the night sky isn't uniformly bright as the surface of the sun is actually our source of our first concern. It is this observation that the night sky is dark and isn't the brightness of the sun that tells us a lot about the universe as a whole, and that we even have night at all is called Olbers Paradox. In 1823, Heinrich Olbers published a paper that asked an incredibly simple question. Why is the sky dark at night? Olbers, he reasoned that if there were an infinite number of stars in the sky, then no matter where we look in space, our line of sight should eventually terminate in a star. So the sky should be everywhere bright. That logic is sound, but the sky is not bright at night. So what's the deal? Now, Olbers' idea didn't come out of nowhere. When Copernicus developed his heliocentric model in 1514, he relegated the stars to a celestial sphere of extraordinary distance. But this idea was extremely controversial, and it was controversial enough at the time for him to wait to publish it after his death in 1543. Further, when De Revolutionibus Orbium Celestum was published, it contained an anonymous, unauthorized preface by one of his fellow theologians and a good friend, and it was designed to obviously soften the blow of the Catholic Church. The preface that this person put was stated that Copernicus wrote his heliocentric account of the Earth's movement as a mathematical hypothesis and not an account that contained any shred of truth or probability. Copernicus's idea contradicted the Old Testament's account of the sun's movement around the earth in Joshua 10:12-13. However, there was no evidence at all that Copernicus himself considered the heliocentric model as merely mathematically convenient or separate from reality. He was just being a smart rabbit and trying to make sure his idea get out there, but that he wouldn't face excommunication. That's why he published it after his death. And that it was published at all was a testament to his good standing as a theologian and church leader. It also testifies to his reputation as a sound thinker. The upshot of his work, though, is that the sky was broken by a moving Earth. Only 30 years after Copernicus's death in 1576, Thomas Digges published a new edition of his father's astronomical almanac, and he has published a bunch of appendices with it. And the most important of them was called A Perfect Description of the Celestial Orbs to the Most Ancient Doctrine of the Pythagoreans, lately revived by Copernicus and by geometrical demonstrations. So his father's original book, his father's almanac, was proposed the Ptolemaic geocentric cosmology. But the appendix that Thomas Digges put in there detailed a discussion of this controversial and still poorly known Copernican heliocentric model for the universe. And in fact, this was the first publication of that model in English, an incredibly important thing in the popularization of science. Thomas Digges's appendix was really just kind of a loose translation into English of some of the chapters of Revolutionibus Orbium Celestum. But in particular, he stated, this orb of stars fixed infinitely up, extends itself in altitude spherically and therefore immovable, the palace of felicity garnished with perpetual shining glorious lights innumerable, far excelling our sun both in quantity and quality, the very court of celestial angels, devoid of grief and replenished with perfect endless joy, the habitable for the elect. Wow, that's some amazing stuff to say. There are stars going out to infinity. Thomas Digges therefore extended Copernicus's idea by proposing that the universe was infinite and contained infinitely many stars. And this idea predated Giordano Bruno. It was in 1584 and William Gilbert in 1600. Copernicus, taking the Earth out of its special place, which really wasn't that good of a place in medieval theology. He had opened the door for an infinite universe. So with this in mind, how bright should the sky be in an infinite universe? Well, let's note what the rough number density of stars are that there are in the universe, and that number, which I'm going to note here with n sub star, is approximately 10 to the ninth stars per cubic megaparsec. That's a lot. So it's about 1 billion stars per cubic megaparsec. That takes into account the idea that galaxies are hubs of stars, but they're not distributed evenly. We're going to pretend that we don't know galaxies exist and that stars are distributed evenly throughout the cosmos. That would be fitting for this time period and this early of Olbers' idea. Now let's get the typical radius of a star, and we'll determine that to be just like the sun. Well, we could use any old value, and since we know that red dwarfs make up the vast majority of stars, we could use that, but for simplicity's sake, let's just use the sun. And it won't alter our eventual result except by maybe a factor of 2 to 10 or something, but it won't change the real result. So if we take the radius of a star, which is approximately the radius of the sun, that's about 7 times 10 to the 7th meters, or if you will, 2.3 times 10 to the minus 14th megaparsecs. Stars have really small radii when measured in megaparsecs. All right, so now let's look out into space and we make a cylinder. If we make a cylinder with radius r star, and we make that very, 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 very long cylinder, how many stars will be in there? And that is given by the number capital N, which is the same as the volume of the stars, volume of the cylinder V, times the number density of stars, N sub star. And the volume of a cylinder is, of course, lambda pi r squared, where lambda is the length of the cylinder and pi r sub star squared is the one of the circular ends of the cylinder. And that gives us the total number of stars that are in that volume. So when we look out through such a volume, we're going to see stars. Now we only need to see what the volume of the cylinder is for one star to be in the way on average. So let's set that big capital N equal to 1 and solve for that for the length of the cylinder, because that's really what we're trying to say is how far can we see? And so the length of the cylinder is lambda, and that's equal to 1, where the 1 is now meaning 1 star per volume, which is out of the number density times the radius squared. Pi r squared times that number density. So really what we're turning is a volume density into a surface density. Again, we're going to use n stars equal to 10 to the ninth cubic stars per cubic megaparsec, and pi r sub star squared is approximately pi r sub sun squared, which is in units of megaparsecs, about 10 to the minus 27th square megaparsecs. So it's a really tiny aspect of a megaparsec. So lambda then, when we plug these numbers in, is 1 over those two numbers combined, and that gives us 10 to the 18th megaparsecs. So that's a distance. That's a really long distance. So 10 to the 18th megaparsecs is really quite big, but it's not infinite. And for comparisons of numbers to show how finite this number really is, the total number of cells in your body is about 36 trillion, or about, we'll call it 4 times 10 to the 13th. So the total number of human cells in a medium-sized American city is about 10 to the 18th. That's definitively finite. Still, 10 to the 18th megaparsecs is much, 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 much bigger than the Hubble length. This means that if the universe were at least that big in radius, then we should see a star in every direction we look, and the sky would be paved with stars. Now we have to ask the question, how bright is this paved sky? Doesn't the brightness of some light source dim with the distance? It does, but these stars are not points. They have an area, so we need to translate that area into some angular size. And it's not just a linear angular size, but an angular area. Angular areas are measured in steradians. There are 4 pi steradians of angle on the surface of any sphere, as viewed from the inside. From the center of the sphere looking out, there are 4 pi steradians. So if the star is really, really, really far away, then you can be considered to be a flat disk on the surface of our angular measuring sphere. And so then we get this omega equals pi r star squared over r squared. Omega is the steradian angle from which the light is coming to us as seen in the sky. The physical area of the star is pi r squared, so r star squared. That's the profile that we see, the physical area. And the distance to the star is little r squared. Uh, that equation is pretty good when the star is really far away and you can approximate half of a sphere of a star with a disk. So thus it subtends a very small aerial angle. And a star has a given luminosity, and the flux will be the luminosity distributed over the sphere at some distance from the star, and that flux is usually F, and that's equal to L sub star, the luminosity of the star, divided by 4 pi r squared, where r is the distance from that star, and flux is measured in joules per second per unit area. And that's usually per unit area on the surface of a sphere that is centered on the source of the luminosity. Well, that distance can be from the star, whether it's in 10 meters or 10 astronomical units or 10 to the 18th megaparsecs. Now, the surface brightness of that one star is measured in watts per square meter per steradian. Now, the area might be the pupil of your eye or a primary mirror of some big telescope like the James Webb. Surface brightness is the relationship between how the light is distributed from the source out to some distance and the size in the sky we see that source to be at that distance. Flux is power spreading out from the source to the observer, and the angular size is the observer seeing how big the source appears to be. Now, it could be that you're making the mistake that the surface brightness is how bright is the surface of the sun or whatever. That's luminosity. This surface brightness is the brightness on the surface of the celestial sphere, meaning our view of the entire sky. So the surface brightness of the one star is the flux per steradian. And that's what the sigma is. It's usually used as surface brightness. So sigma sub star is equal to the flux F divided by omega, which is the steradian angle. And we can see that we plug in those two other things before, and we end with L sub star divided by 4 pi squared, r sub star squared. All right, what's really interesting here is that the surface brightness does not depend on the distance to the star and only the star's luminosity and its radius. So the surface brightness of an infinite sky paved with stars, or at least a universe 10 to the 18th megaparsecs in any direction, will be as bright as the disk of the sun. This, of course, is complete bonkers nonsense, as you can totally understand. Well, it's not just that it sounds bonkers. How bonkers is it? We need to quantify our bonkerhood. The surface brightness of the sun, sigma sub sun, is about 5 times 10 to the minus 4th watts per square meter per arc second squared. And the surface brightness of the dark night sky is 5 times 10 to the minus 17th watts per meter squared per arc second squared. And so our estimate is off by a factor of 10 trillion. So we got to have something wrong with some assumption somewhere. And let's look at all those assumptions and see where we went wrong. Okay, our assumptions are the following. 1, the universe is completely transparent. 2, the universe is infinitely large. 3, the universe is infinitely old. 4, the surface brightness of a star is independent of its distance. And 5, light doesn't lose any energy as it traverses the static universe. Let's look at each in turn. First, let's look at the transparency. Okay, so let's say the universe has something blocking it. And originally, that's how a lot of people thought this would be resolved. So that opaque something would absorb that light because it's absorbing it because it's opaque. And eventually, over time, something that's opaque will heat up. And therefore, the thing that's in front of all that starlight will eventually heat up until that thing is just as hot as the ambient starlight. And therefore, you have the same problem over again. So it doesn't matter whether it's completely transparent. In fact, that doesn't work at all. Next, the universe is infinitely large. Let's look at that one. If the universe has a finite size. Let's just pause it for just a second. If it has a finite size, then only a fraction of the sky would be covered. Let's say the universe is literally a box, and whatever's outside the box, we don't know, we don't care. So the fraction of the sky would be covered because there's only so many stars inside a finite box. But if it's infinite, but past that point there are no stars, okay, well, that's the same kind of thing as if it's infinite, but there's nothing past that. And then we would be just happening to live amongst the only island of stars, which seems a little weird. So there's some things that could be wrong with it being infinitely large. Next, let's look at the assumption of the infinite age. Well, perhaps we can violate that by saying we live in a really special time, in this ageless time where stars truly now exist. And before then, they didn't. Or if the universe has a finite age where, say, some t sub naught, that's the finite age, is much less than the size, lambda, divided by the speed of light. If that's the case, then due to light's finite speed, we could only see stars out to some maximum distance, r, which is about the speed of light times this age, t sub naught. And only some fraction of the sky will then therefore be covered, which would be f, would be that fraction that's roughly the same as the speed of light times the age of the universe divided by the distance of the universe. So that'll be some fraction of the universe would be covered. Next, we have to look at the surface brightness of a star being independent of its distance. In an expanding universe, the surface brightness would drop with distance compared to a static universe envisioned of an infinite static universe. And if we're contracting, things would be brighter than expected. So maybe this expanding universe will get rid of it too. Next, let's look at light not losing energy as it traverses the universe. Okay, so it does lose energy due to the cosmic redshift, but let's say you believe the universe is not expanding. So light maybe would get tired as it travels and lose energy. And this tired light idea is kind of new, and it's not at all supported by observations. First, tired light can't replicate the blackbody spectrum of the cosmic microwave background. Without the expansion, every photon in the universe must lose energy in a way that preserves the perfect blackbody spectrum. This is kind of improbable, since every photon would have to know what every other photon is doing in the entire universe. And that's kind of a big call for 10 to the 89th cosmic microwave background photons. All right. So also, tired light can't explain the time dilation of high redshift supernovae. If tired light was a thing, then the light curves of supernovae would be distance independent. And they're simply not. They're stretched out. The farther away they are, the more stretched out the supernova light curve is. Next, tired light would change the photon's momentum and blur distant objects because if you change the energy of a photon, you do change its momentum. And momentum has a directional component. So therefore, it would blur the distant objects. It's not seen. So tired light would also alter the surface brightnesses of galaxies in a way that's not observed, i.e. making them distance independent. This isn't seen due to the expansion of the universe that we know exists. So how is Olbers Paradox actually resolved? And I'm just going to give it away. The resolution is principally due to a finite age of the universe. The light from the horizon distance simply has not had time to reach us yet. And the horizon that I'm talking about is not a boundary or an edge. It's not something that if you went up to it and you would fall through or punch through. It's not like this depiction from the 1888 Flammarion engraving. This kind of edge boundary simply does not exist. It's just the place from which we've been able to get light. So that's what we mean by the horizon distance of the cosmos. The currently understood horizon distance, I'm going to use Planck mission's value for the Hubble constant, which is 67.8 kilometers per second per megaparsec. And that gives us a horizon distance of approximately 14.42 gigalight years, or about 4.4 gigaparsecs. And this distance is, of course, a lot smaller than infinity and a lot smaller than 10 to the 18th megaparsecs. Yeah, I kind of alluded to Hubble constant. We'll get into the Hubble tension later. Just to close this thing out, it's kind of funny that in 1848, Edgar Allan Poe chimed in with a correct interpretation from his Eureka, a Prose Poem. No astronomical fallacy is more untenable, and none has been more pertinaciously adhered to than that of the absolute illimitation of the universe of stars. Were the succession of stars endless, then the background of the sky would present us an uniform luminosity, like that displayed by the galaxy, since there could be absolutely no point in all that background which would not exist a star. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions, would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. Well, that raven didn't need to speak too much more on that topic, now did it? Well, so much for the night sky. There's a night sky, and we can solve it by understanding that the universe has a finite age. I'd like to thank all my Patreon supporters for their support. It's been great having their help in this and their support, and I hope you would like to become one too. In the meantime, please subscribe and like this channel and like this video, and please share it around because I'm going to be doing the entire textbook from Dr. Barbara Ryden's Introductory to Cosmology. And this is just the second of many innumerable videos I will be doing on cosmology from this textbook. And we'll see you next time. Hello, this is Jason Kendall, and welcome to the next in my cosmology series. If you're just tuning in, please go and look at my playlist on my YouTube channel about the cosmology series, so you can start at the very beginning. We're into chapter 2 and section 2. This is about the fundamental observations of the cosmos, and we're talking about homogeneity and isotropy. So what exactly is homogeneity and isotropy? Let's look at some examples. Let's say you're in a big forest and you look in any direction. No matter which direction you look, you're going to see a tree. And so from a directional perspective on the floor of the forest, it's isotropic with respect to trees. So some trees are closer, of course, closer than others, and so they look bigger, but every tree, no matter what, in every direction, you're going to see a tree. Also, if the forest is really big, it doesn't matter where you're looking from inside the forest. You're just going to see a bunch of trees around you. And in fact, everywhere you go, you're going to see trees that look bigger because they're closer to you, and they won't be really small if you go over there simply because they look small to your eye here. No, they will be roughly the same size and roughly the same place. However, we notice that if we look up, this violates it, and if we look down, it violates it. So we're looking mostly straight through the forest to see exactly what we mean. Therefore, homogeneity and isotropy are not the same thing, and they don't imply each other. One is where we stand, and the other is where we look. Where we look is isotropy. When we look out into a particular direction and see the same thing in any direction, that is isotropy. And that's what we can think about as the center of this bullseye here. So if you're standing at the center and looking in any direction, you're going to see the same thing in every direction. However, that's not homogeneous. If you weren't at the center, you could tell which direction is preferred simply because, well, you could see a different arc of things, and maybe you'll see a line of purple and blue, and the radius of curvature of the lines will change as you get farther and farther away. So it's not isotropic, but it's isotropic around one point, and it is not isotropic anywhere else. The lines that we see on the right, those lines are homogeneous, but they're not isotropic, meaning no matter where you go, let's say this is an infinite set of lines, and just in the same way the bullseye we can think is infinite, but if it's an infinite set of lines, then no matter where you drop, you're always going to see the same structure of lines. But there's a preferred direction of up and down, so that violates isotropy. It'll be homogeneous, meaning it's roughly the same stuff wherever you stand, but it doesn't look the same in every direction. So therefore, isotropy is about which direction we're looking, and homogeneity is what's it like right around us where we're standing. Isotropy itself, cosmologically, because that's what we really care about now, is the isotropy and homogeneity of the cosmos. Isotropy only works on the largest size scales. So what does that mean? Okay, so let's take a view from, then try to find directional things of what we mean by isotropy in the universe. When you look at the Earth-Moon system, which is about 200,000 miles across, there's a preferred direction from the Earth towards the Moon. So that is definitively not isotropic. And if we scale it out a bit bigger to a couple of astronomical units, it's still not isotropic because the sun provides a preferred direction. And if you don't know what that means, just look up on a sunny day and you see the sun. There's your preferred direction towards the sun. And if we went out to about 50 or so astronomical units, included most of the outer solar system, it's still not isotropic because there's still the sun and there's a disk-like shape, which is the plane of the solar system. That's not isotropic because up and down are different than side to side. Now, if we look at the scattering of nearby stars within a few parsecs or so, it looks kind of isotropic-ish on a few parsecs out to the nearest stars, but we can make out a preferred direction out of that big thing off to this direction about 10,000 light years away, the center of the Milky Way. And the Milky Way itself is not isotropic because it's a disk shape and there is a center. So in our perspective of, yeah, if you were at the center of the Milky Way, it might look isotropic in the same sense as that target, but up and down out of the plane of the Milky Way is certainly not isotropic. And this is on size scales of about 100,000 light years. So let's go bigger. If we then go out to a few megaparsecs, about 3 or so megaparsecs, we are including the local group of galaxies. That would be the Andromeda Galaxy, Milky Way, the Triangulum, and others. But this is still not isotropic because we can make a preferred direction, the line between the Milky Way and Andromeda, and that still gets us a non-preferred direction. So let's get even bigger scales. Our local Laniakea supercluster encompasses about 100,000 galaxies stretched over 160 megaparsecs, or almost 500 million light years. It's about 100,000 times the mass of our galaxy, and it has about 4 separate subclusters that once were called separate superclusters. But we can still define a center of mass to this supercluster and then show some sort of orientation. Let's get bigger. Now, if we look at the size scales of greater than about 200 megaparsecs, or greater than 500 million light years, we don't find any extra large grade A super duper plus size superclusters. So the biggest superclusters are about 200 megaparsecs in size. That means we're now discovering roughly the scale of the isotropy of the cosmos. And if we get out to look at the observable universe, we see that it's about 30 gigaparsecs across from the one side of the observable universe to the other, is about 30 gigaparsecs. And it's certainly isotropic around the center of the diagram, and it also seems to be hinting about isotropy elsewhere inside of there, meaning it doesn't seem to be a preferred place. So we definitely are seeing isotropy on the largest size scales of 200 or so megaparsecs out to the observable universe. What we were looking at before was just simply a diagram. So where does this kind of information come from? Well, it comes from things like the 2DF Galaxy Redshift survey, which shows the distances and positions of galaxies in the cosmos out to a limiting magnitude or limiting redshift and therefore a limiting distance. So the surveys themselves tend to be kind of pencil beam and narrow. So if you were to look at them, they kind of look like pizza wedges because we're looking at a narrow band of sky, but scanning across. So it allows us to see what these galaxies are in a given direction. Now, if you look at this survey, we see that from the center, the vertex, where we are looking outwards, we see that roughly the same things are in roughly every direction, no matter what, when we look out from the center of there. So the isotropy itself statistically looks from one angle, one direction to another, roughly the same on the size scales of about 500 million light years, or about 200 megaparsecs. And that's what we see. We see groups punctuated by voids, punctuated by groups, punctuated by voids. And so it's roughly the same stuff in every direction that we see. And this is true for almost every galaxy redshift survey that's been done. Well, not for almost every, it's been true for every galaxy survey that's been done, such as the Sloan Digital Sky Survey and others. Isotropy is actually best confirmed on the cosmic size scales through the cosmic microwave background. The current state of observational work has spectacularly confirmed and greatly strengthened the observational case for the Big Bang standard model of cosmology. The cosmic microwave background shows a perfect blackbody spectrum no matter the angle you're looking. It's characterized by a single temperature across the entire sky of 2.725 Kelvin, plus or minus 1,000th of a degree. It uniformly fills the universe, and the variations in the temperature that you see in this map for the Planck mission that was released in 2018 is that this is better. These differences in temperature between the red and the blue are 1 part in 100,000. And these then become the seeds for large-scale formation and galaxy structures later on in the universe's history. So this is truly the test of isotropy. The anisotropies in the universe of the cosmic microwave background are 1 part in 100,000. Now, you might think, oh, it's just the Planck mission. Well, it's not unique. This started with the observation by Penzias and Wilson. There were other ground-based observing structures, to balloon-based experiments, to space-based observatories with the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, ESA's Planck, a number of missions and experiments conducted at the South Pole and northern Chile. They've all confirmed the isotropy of the cosmic microwave background, which reflects the isotropy of the universe as a whole. Now let's take a look at homogeneity. Homogeneity is a lot trickier to observe because homogeneity says where you're standing, right? So we can't really move 200 megaparsecs to the right or anything. So that's really hard. So let's look at it from a slightly different perspective. Consider the average density of the universe. According to the Planck data, the Planck cosmic microwave background data, the Hubble constant today is about 66.88 kilometers per second per megaparsec. And that gives the critical density, meaning the difference between an open and a closed geometry universe, and a critical density of approximately 8.4 times 10 to the minus 27th kilograms per cubic meter. That's really nothing. That's only a few protons every square meter, right? That's really not much. So the baryon density is a tiny fraction of that. It's 2% of that, which is 1.86 times 10 to the minus 28th kilograms per cubic meter. And that's one proton for every 4 cubic meters. That's what the mass is, that's what it works out to be. So that's a very, very, very low density. Let's see how that works out. Locally around U, so we're going to try to determine how good our homogeneity is by saying, are we typical of the density of the average universe? Locally, you're about, right around U is about 100 kilograms inside a cubic meter centered on U. So no, it's a pretty big compared to the average cosmic density. If we then look at the average density of the Earth as a whole, that's about 5514 kilograms per cubic meter. That's still way, way, way too large, much bigger than about 2 times 10 to the minus 28th. Let's now expand the idea and look at the inner solar system and take about a couple of astronomical units out and look at mostly the mass of the sun that's inside of there. That drops the density down to about 5 times 10 to the minus 6 kilograms per cubic meter, but still that's really large. Let's get our size scale even bigger. Take the entire Milky Way, which has a mass of about 6 times 10 to the 42nd kilograms, And the volume of the Milky Way, which is a disk with a bulge in the middle, that's about 7 times 10 to the 60th cubic meters. Now we're getting close, but we're still not there. That's about 8.5 times 10 to the minus 19th kilograms per cubic meter. And still, that's a billion times too dense. Now let's grow our size scale out to the local group, where it's about 1.3 times 10 to the minus 27th kilograms per cubic meter. And that's about 10 times still too big than the average density in baryons, in only baryons in normal matter. The density of the local group would of course include dark matter. So that's going to be large. I'm looking specifically at matching the baryonic homogeneity only on the size scales of superclusters. Once we're looking at 200 megaparsecs or so, does the baryonic density drop to the cosmic average when we start to figure that in? Otherwise, the homogeneity, we don't get to that point. Why we use density is because homogeneity means even mixing. So if you mixed everything out evenly and took an average, that's another way of looking at homogeneity. So only on the size scales of superclusters of galaxies does it finally drop to that cosmic average. Now, because we're looking at homogeneity as a cosmic average of stuff, that means that if we're looking at stuff, then stuff probably behaves the same everywhere. So homogeneity has a very interesting implication. And that means that the same physical laws apply everywhere in the entire universe. And that we can actually see in the great distance that things look roughly like galaxies and expanding clouds of hydrogen gas, and we can explain things with black holes and star formation. That's actually a really good, powerful assumption that it lends credence to this idea. And so far, no observation yet has invalidated our understanding that current physics that we know locally, locally means out to a few, even megaparsecs, is that we can't apply it to the rest of the universe. This leads us to the core central idea of all cosmological study, and this is the cosmological principle. We're going to first start with the Copernican principle that says that there's nothing special about our location in the universe other than the fact that this is the place where we call home and it's where we live. But if you take isotropy around any point in the universe, and we've spectacularly confirmed it with the cosmic microwave background, and you combine that with the Copernican principle that says there's nothing special about our location, then that means isotropy around one there's isotropy everywhere, around every point in the universe. And so isotropy everywhere means homogeneity everywhere. Therefore, combining the Copernican principle with isotropy around any one point means it's homogeneous in the universe. The cosmological principle is therefore that the universe is everywhere isotropic and homogeneous. This means that anyone, any observer, anywhere would see roughly what we see, no matter where they looked. And that's a very important point. Everybody and every observer sees exactly the same thing. Now, the cosmological principle says that everybody everywhere says everything. But there's also a concept where we can call it the perfect cosmological principle, that everybody everywhere everywhen sees the same thing. So therefore, we take the Copernican idea that not only are we in a special place, but we're not in a special time. And if we are not in a special time, that implies the steady state model of cosmology. And the steady state cosmological model has, unfortunately, even though it's a very elegant model, there's a lot of evidence against it. The cosmic microwave background was the first that put the steady state model to bed because there's nothing inside of the steady state models that can actually create a proper cosmic microwave background. Also, later, the galaxy evolution surveys, such as the Hubble Ultra Deep Field that's seen here, where as you examine this pencil beam survey of the Hubble Deep Field, you see foreground galaxies that look highly evolved and background galaxies which are tinier, redder, and much more misshapen. So there is a progression of galaxies from then to now, meaning we don't see, if the steady state was true and there was no special place in time, then if we look in the Hubble Deep Field, we should see things exactly like the Milky Way, no matter how far away we look. And we simply don't see that. So the perfect cosmological principle is false, and along with it, the steady state model. There are also some amazing philosophical implications to the Copernican principle. It asks us to permanently change our understanding and view of the specialness of humanity. Every single advancement in the understanding of science and technology, and many things in the arts and the letters, has helped make us less special in the universe. And I don't mean less special like as in we're not special because we're alive or we're unique individuals or that dolphins are really cool or spiders are cool or any of that stuff. No, we're not special because we're not unique. Once we discovered atoms, the discovery of atoms showed that everything's made up of atoms, including us. The discovery of the distances to the stars said, wait a second, that bright disk in the sky, that sun thing, that's those points of light that are way up there in the night sky. They're just like the sun, but very far away. When we discovered that humans and other primates are very similar, in fact, we have some deep similarities to even trees, that showed us that we're not really that special. More recently, we discovered exoplanets, planets around other stars, which shows that Earth and Venus and Mars and Jupiter aren't unique. There's planets everywhere. And in fact, the James Webb Space Telescope is currently available to observers who are making proposals and get it done, but it's able to see spectra of planets in the habitable zones of nearby stars. And so we might find in the next decade or so that life itself in the universe isn't special either, and that the Earth does not hold a monopoly on life. Now, I'm going to probably say that if we're going to say the nature of homogeneity, my personal bet is that there's one sentient life form that can understand, well, this particular YouTube channel within 200 megaparsecs, and you're part of it. I think that sentient life is extraordinarily unique, but if we take 200 megaparsec size scales, maybe there's one in each. That would be a good size scale. Give me a couple 100,000 galaxies and with trillions and trillions of stars and trillions upon trillions of planets, then we're starting to have the chances for life to rise into sentient nature again elsewhere in the cosmos. But life itself, finding bacteria, we're going to find that. We're going to find that probably around either on Mars or maybe in Enceladus or in Titan, but probably around some other planet sometime in the next 20 years or so. These philosophical implications of the Copernican principle just says that we're not special and we're in no special place. And that's what we mean by the isotropy and homogeneity of the cosmos. For cosmology, it means that the same physical laws apply everywhere in the universe, that every observer will see everything the same way we see it, no matter where they're located in the cosmos. Not when, today is different than ago, but no matter where you are in the universe, that's what you'll see. So the law of the universe's redshift is expansion that you'll see anywhere in the universe. The cosmic microwave background, we'll see it anywhere in the universe. Galactic evolution, you'll see that anywhere in the universe. Cosmology relies on this Copernican principle and the cosmological principle to show that the universe is homogeneous and isotropic. And in fact, we have observational evidence for those things. And thanks for watching. I just want to take a second and thank my Patreon supporters who've been fantastic for all this. They're giving me a lot of support. And if you would like to join me and get some preview content, please become a Patreon subscriber. Also, if you like this, please do hit that like button and subscribe to the channel, because I'm going through the entire textbook of Barbara Ryden's cosmology book, and it's going to be a long ride. And this is the third of many videos. And we'll see you next time. Hi, this is Jason, and welcome to the next of the videos in my cosmology series. Just to let you know where we're at, this is all about a textbook from Dr. Barbara Ryden, her Introductory to Cosmology, and so we're going to be following through that entire textbook. And if you're just jumping in the middle, please look at the link to the playlist below. That'll show you where you should start so you can get the thing from the very beginning. All right, so what we're looking at this time is chapter 2, the third section, which is redshift. And redshift is proportional to the distance, which is an incredibly important fundamental observation for cosmology. All right, let's get to it. Redshift, what is it? Let's define this to be this letter Z that you see here. It is the observed wavelength minus the emitted wavelength divided by the emitted wavelength. What does that actually mean? What it means is that if there's a relative motion between the observer and the emitter of this, whatever light it might happen to be, then the wavelength of light will be changed from its emitted wavelength to its observed wavelength. So if it's moving away from us, we should see it be redshift. If it's moving towards us, it should be blue shifted, meaning going towards shorter wavelengths. Redshift means longer wavelengths. So when we look at, say, this galaxy, which is NGC 1068, we see these pink glows in there, and those are from hydrogen gas. And those hydrogen gas clouds are where stars are being formed. And in the center of it, we see that there's some very bright emission lines of hydrogen and helium and oxygen, because this is a starburst galaxy. And in fact, it is an active galactic nucleus. And so when we look at the spectrum below, we see a bright hydrogen emission line right around 6550 angstroms. And this galaxy has a redshift of 0.003793, according to the the NASA Extragalactic Database. And so this emission wavelength of hydrogen, which is H alpha, which is 6562.81 angstroms, that's been redded to the observational wavelength of 6587.74 angstroms. So its wavelength has been lengthened by 25 angstroms. And that's important because that's what the observed wavelength is longer than the emitted wavelength. Remember that what's important here is we see this picture of a galaxy. And this galaxy is far, far, far away, extremely far away, millions of light years away. And yet we are saying that the laws of physics over there in that galaxy are the same that we measure here. And this is the cosmological principle that we talked about before, and that we're nowhere special, meaning the laws of physics are the same there as here. And this spectrum was taken by Moustakis and Kennicott, published in Astrophysical Supplement in May of 2006 in a study of active galactic nuclei. Now, the study of extragalactic redshift began in the 1910s. Vesto Slipher at the Lowell Observatory was doing some incredibly important work in astronomy. In 1912, he was the first person to observe the shift of spectral lines of galaxies, meaning he's the first person to make the observations like the ones we saw in the previous slide. And it makes he's the person who discovered galactic redshifts. And he said they were a Doppler shift, and he said there were some subtle changes and so forth. He thought it was a Doppler shift, and he measured the speeds of the spiral nebulae that he found. And there you can see the various nebulae that he looked at, and there was 10 that are close by. And these are all redshifts. Of the 25 spiral nebulae, and he called them spiral nebulae at the time, not galaxies. He called them spiral nebulae because they were nebulous clouds in his imagery, and they looked spirally. So of these 25, 21 showed a redshift, with some with high speeds, as you can see from this graph, up to 1,000 kilometers per second. And that's huge. The redshift was interpreted by him as a Doppler shift. And when you look closely, you see NGC 224. That is Messier object number 31, which is the Andromeda galaxy. It shows a blue shift. That's why it's labeled the negative there. It's one of the very, very, very few that actually show a blue shift. Now, Vesto Slipher was one of the most important people in history of astronomy because he's the one that opened the door for us to understand that these nebulae were not part of the Milky Way. And at that time, it was thought that the entire universe was only the Milky Way galaxy. And so he thought that they were probably not part of the Milky Way, but he couldn't be conclusive about it. He also discovered rotation in 1914 of these spiral galaxies, or nebulae, simply because he was able to take spectroscopy of it. And on a very personal note, he was responsible for hiring Clyde Tombaugh to make the discovery of Pluto in 1930. And I remember Clyde Tombaugh from my time in graduate school in 1990. He was an old man, and he was a wonderful old guy. I'm glad to have met Clyde back when I was in grad school at Las Cruces, New Mexico. Now, an important thing about the nature of the redshifts that Vesto Slipher found was that this was something he put out there, and people really were understanding what was going on at the time. And Einstein's relativity was playing a huge part in the physics community at the time. Georges Lemaitre, who was a Catholic priest, he was also a physicist, a mathematician, astronomer, and a professor of physics at Catholic University of Louvain. He compiled a list of the 42 galaxies whose Doppler shifts had been measured. And he theorized that the recession of these nearby spiral nebulae or galaxies could be explained by an expanding universe, which was going to be confirmed by Edwin Hubble later. But he found that in his list, 37 had redshifts and 5 had blue shifts. And let's just see how probable that is just by chance, because if you took a random sample of the sky and then say 42 galaxies out of the random sample in the sky, and if it was totally random, you might expect half to be coming towards us and half to be going away from us. But to think if it's completely randomly distributed velocity speeds, and 37 of them had redshifts and 5 had blue, let's just take this like we had 42 coin tosses. What are the chances that if you flipped a coin 42 times, 37 times it would come up as heads and 5 times as tails? Well, the probability for that is about 2 times 10 to the minus 27th. That's a very, very, very tiny probability. So this was not random. This is not a random thing. This is some systematic thing. And he made an average radial velocity of all of these and said, well, let's just say it's an average. And the average then said, from his perspective, about 600 kilometers per second. And he used Vesto Slipher's data as well as others in 1927. And he pointed out that this could be resulting from an expanding universe, which he derived from Einstein's relativity. Now, the funny thing is that Einstein, at first, when he learned about Lemaitre's conclusions, he refused to accept the ideas because he said that while his calculations were good, Einstein was fully fixed on the idea of a static universe at the time, which was fixed by a cosmological constant, and that was Einstein's idea. But Lemaitre came up with this idea and found an estimate for the average distance. And he said, well, if the average distance of these things is just under a megaparsec, say 0.95 megaparsecs, for all these galaxies, along with this expansion of using this as an expanding universe, it gives him basically a Hubble parameter or a Hubble-Lemaitre parameter of 625 kilometers per second per megaparsecs. And this is basically the first measure of the Hubble constant. He derived this Hubble's law, then, therefore, and it's now called, as by agreement by the International Astronomical Union in 2018, that it should now be called the Hubble-Lemaitre law. And it was the first estimation of the Hubble constant. And this is 2 years before Hubble derived his article in 1927. Lemaitre also proposed the Big Bang theory of the origin of the universe, calling it the hypothesis of the primeval atom and also calling it the beginning of the world. And he was greeted with a lot of skepticism at the time. However, when he passed away in June of 1966, he had learned about the discovery of the cosmic microwave background. And this provided further evidence for his original idea and proposal way back in the 1920s. So this is an amazing person who started the ball rolling. Next, we go to Edwin Hubble. Edwin Hubble arrived at Mount Wilson Observatory, which is in Southern California, in 1919, right around the time the 100-inch telescope was completed on Mount Wilson Observatory. At the time that he arrived, the prevailing view of the cosmos, again, was that the universe was entirely composed of only the Milky Way galaxy. He then looked at the objects that were seen as spiral nebulae with these recession velocities, and he identified Cepheid variables inside of these objects. And Cepheid variables were a standard candle that was discovered by Henrietta Leavitt in her studies of globular clusters. What he found was that if he compared the apparent luminosity to their intrinsic luminosity, that would give the distance from the Earth. And the intrinsic luminosity is dependent on the period of their variability. So you can see here, there's an image of M31, which there's a discovery of one of these variables in 1923 in October, and he followed these variables night after night after night to finding their period of variability. And you can see that in those sawtooth patterns. You can see how long it takes for them to get bright and dim, and that's the light curve. And from peak to peak, the brighter it is, the longer the just time between peaks. So this is a very well calibrated distance indicator. And so we used that, found the Cepheids in distant galaxies, used those distant galaxies then to get the graph that we see from his publication in the Proceedings of the National Academy of Sciences in 1929. And what we see is he has found the recession velocity as a function of the distance. Now, he wasn't really sure of the expanding universe, but he was very trepidatious about this at the time. But he did make the good observations and found Cepheids in all of these spiral nebulae, which we will soon call galaxies, including the Andromeda Galaxy and the Triangulum. And his observations proved conclusively that these things were far too distant to be part of the Milky Way, and therefore were in fact galaxies outside our own. And today we no longer consider them nebulae. The slope of the line that he found with these galaxies, given the distance he found and this recession speed, worked out to be about 500 kilometers per second per megaparsec. And that leads us to the Hubble law, or more specifically the Hubble-Lemaitre law, which shows that the velocity, v, is equal to this Hubble constant, h sub naught, times the distance, which is now labeled r. And so we could actually put the redshift in there, which is z, and then that's equal to the Hubble constant divided by the speed of light times the distance as well. But the radial velocity is a function, assuming, so the redshift can be interpreted as a radial velocity or a Doppler shift, and that's where the z becomes v, because z is just the shift in wavelength, but we don't know what the function is. But if we interpret it as a Doppler shift, then we can convert it to that v over c. All right, so this is Hubble's definition, and his first derived value based on observations that he did was 500 kilometers per second per megaparsec. Georges Lemaitre made an assumption for a distance of about a megaparsec and got a much higher value. The value for the Hubble constant would be debated for a very long time until it winnowed down to a narrow set of values. Now we're left with two different values for it. But this Hubble law is valid only for nearby galaxies. The farther away we go, we have to use a relativistic version of the Doppler shift. It's also really important to note that, again, the Hubble law, the Hubble-Lemaitre law, basically says the farther something is away, the faster it's rushing away from us in this linear fashion. For every megaparsec it's away from us, it is traveling, say, 60 or 70 kilometers per second faster for every megaparsec distant. So the distance is proportional to the redshift. And the farther it is away, the faster it's rushing away from us. Let's see what the implications of that are right now. So what are some of those values for the Hubble constant that we see before? Now, if we look at these three diagrams, we see first on the left, publication proceedings from the National Academy of Sciences in 2004. We see that the Hubble diagram for using type 1a supernova as the distance indicator. So there was definitely a recession velocity, and we see the recession velocity as a function of distance, and it's definitely on a line out to about just under a gigaparsec, out to 700 megaparsecs. Hubble's original data is a little red square in the lower left-hand corner. And so we can see that this Hubble relationship wasn't just for local things, but it actually goes all the way out deep into space of megaparsecs. And it's not just Cepheid variables or type 1a supernovae. As we can see, there's things called the Tully fissure or the fundamental plane or surface brightnesses or type 2 supernovae. And we see the average for the Hubble constant from that particular study of a bunch of things put together to see what the average would be is approximately 72 kilometers per second per megaparsec. That's what we can see in the middle graph. So modern data for Cepheid variables gives a value of about 73 kilometers per second per megaparsec for the Hubble constant. And this agrees well with a lot of other direct measurements, such as these type 1a supernovae, Tully fissure, which is a relationship between the brightness of a galaxy, of a spiral galaxy, and its rotation rate, type 2 supernovae, and other measurements. But it really disagrees, quite importantly, from the cosmic microwave background and baryon acoustic oscillation studies, which show that it's roughly 67 kilometers per second per megaparsec. And these are two well-established ways of measuring these this expansion rate. And they're in direct conflict. And this is known as the Hubble tension. And this conflict is valid to within 4 sigma. So this is a real thing. So people have to figure out, and so it's an area of active research. Many of the areas of the active research are based off of the Planck data from the ESA's mission, the European Space Agency's Planck mission, which had some of the final results in roughly 2018. And they've been analyzed and combined with many things to find that by 2021, that when you look at the cosmic microwave background implication for it, you get a series of range of values that are right around 67 and a half or 67 and a third or thereabouts. And that's without the Planck data. Cosmic microwave background without the Planck data shows this. WMAP shows this. But if you have, and then you take Big Bang nucleosynthesis arguments with like the baryon acoustic sky survey done by the Sloan group, then you find that there's also this kind of low value. This is really important because the cosmic microwave background and its imprint from the early universe seems to indicate that the Hubble parameter is much lower than if we take more, quote, recent data by direct measurements. The cosmic microwave is an indirect measurement, but the direct measurements, say from Cepheids or Myra-type variables or supernova 1As or masers or the Tully fissure relation, they all definitively show a much larger value of 73.2 or 73 roughly. And that's important. It's also interesting to note that the new gravitational wave astronomy that's coming out can actually provide a direct measurement of the Hubble parameter, and it agrees with both. But in any event, the Hubble tension is a real thing and an area of active research. So we'll use 2 different values for the rest of this to understand the nature of redshift. So there might be some of you around there that says, wait a second, redshift uniformly that we see, and the farther away something is, the faster it seems to be rushing away from us. Wait a second, what is with this Hubble law? Doesn't that violate the cosmological principle? Because we started with this idea ago with the cosmological principle says we have isotropy around one point, combined with the Copernican principle that says that we're not special at any point, implies homogeneity throughout the entire universe. Doesn't this violate the cosmological principle? Because it makes us look like we're a special place, like everything's rushing away from us. And in fact, no, that is exactly the opposite conclusion you should draw. Because if we are not at any special place, then this is exactly what you should see in a homogeneous universe that's expanding uniformly. So if we see it, then it doesn't matter where we are. If we were 200 million light years to the right or left or up, we would still see this thing. And in fact, any observer in the universe anywhere will see this effect. So the cosmological principle is not denied by this. In fact, it's strengthened by this idea. To see the effect of the expansion of the universe in a homogeneous and isotropic way that is uniformly expanding, let's actually make a diagram of, say, 3 galaxies. And each of the galaxies may have started from a distance that's the deep blue triangle in the middle, and then the universe is expanded to the light green triangle. And so each of these galaxies has rushed away on its red arrow from each other. Now, there's not any center to this point. This triangle was completely arbitrary, and if I changed the triangle to a different set of three galaxies in a different place and rotated them differently, it doesn't matter what orientation, where I place the galaxies, anything, there's no center to this expansion. It's a very important thing. An observer in any one of these three galaxies will consider themselves to be at the center of the expansion, just like we do. It's a very important thing. But we're just checking the uniform expansion of space between three of them. So first we define the distances. R sub 1, R sub 2, R sub 1, 2, R sub 2, 3, and R sub 3, 1. Those are each defined by the difference in the vectors. That's what those little bars are. And that's what the vectors are. R1 with a little arrow on it is a vector. Now, it's true that we do have to have some point of origin for every vector. But since we only care about the distance between 2 points, and therefore the difference between two vectors, we actually don't really care about the source or origin point of that vector. In fact, it works out that since there is no center to the expansion of space-time, that we don't really care where we choose the origin for it. And it doesn't matter anyway for this purpose because we only really care about the distances between any two galaxies. R1 minus R2 vector, and the absolute value of that is equal to the distance R1, R2. Same for the other three distances as well. And we let all of those things vary with time. As we let them vary with time, we say now on the right-hand side, those three equations, we show how they vary with time in a uniform and homogeneous manner. So R sub 1, 2 as a function of time is equal to A times some t, well, not times some t, A as a function of time, times the distance that it was at some time initial, t sub 0. And so that A sub t, A of t, scale factor is just the scale factor for the expansion, and all distances grow or shrink at exactly the same rate and with the exact same history. So they all start at some R sub 1, 2 or 2, 3 or 3, 1 at some t naught. We don't care what that time is. It can just be a go, or it can be now and just let it progress into the future. And the scale factor applied to all three is the same. And so that preserves the triangles from the smaller triangle to the bigger triangle. And if we let it go further, the triangle will be preserved as well. All the angles will be preserved. The ratio of the angle, and side rules that you remember from high school geometry, those will all be preserved as time goes on. All right, so now we can then look at the nature of this expansion and how fast things are moving and what the rate of change is. So all of them are going to be having the rate of change being the same, but we can describe v, meaning the velocity of the change, but the v's already have a direction because we have v as measured between galaxy 1 and galaxy 2, and the v measured between 2 and 3 and 3 and 1. All those things are some change in time, dr 2 dt, which is the change in the distance with respect to time. And that's equal to the rate of change time derivative of a of t. And so I've shortened the notation to dot a because that's a standard notation for derivatives with respect to time specifically. And you still multiply that by the initial distance r sub 1, 2 at time initial. So that looks like a whole bunch of things together, but really it's two things. The rate of change to the scale factor, a dot, times the initial distance, which is r1, 2, time of at the time 0. Notice we have three equations. They all have the same exact appearance. But now we take the original equation for the derivation for the distance and we plug that back in, and we find that a dot over a times then r1, 2 of t. So now we're not looking at it from the respect of the initial time, but as it evolves, we have this funny thing in there. So the velocity, the speed, v1, 2 of t, is equal to the distance, 1, 2 of t, as a function of time, times this ratio of the rate of change of the scale factor divided by the scale factor. That a dot over a is called the Hubble parameter, and that's its definition. That is the definition of the Hubble parameter, and it maps the entire history of how these distances all grow or shrink at the same rate because they're all doing so uniformly and homogeneously throughout the universe. Didn't matter which three galaxies we picked. It's just three random galaxies at three random locations. Just because I chose a right triangle doesn't mean anything. But if I chose any 3 points inside of this, I would get exactly the same reaction. We could have just done one just to say that, but then you said, oh, wait, why is it just one? So remember, this triangle could be oriented in any way you can possibly imagine. It will always show this rate. Again, this is the result of the homogeneous isotropic expansion utilizing the cosmological principle we talked about initially. Now, if we look carefully at that Hubble relationship, which is the velocity is equal to some constant times the distance, meaning kilometers per second per megaparsec. And so if you have some distance, you get the Hubble constant and equals the velocity. But if you look closely at it, it's kilometers per second per megaparsec. So we really have kilometers per megaparsec per second is another way of looking at it. But kilometers per megaparsec is that's a distance compared to a distance. So that's some scale factor in there too. That's just changing kilometers per megaparsecs. Therefore, we can then try to solve for a time. So if we take the distance to an object divided by its velocity that's rushing away from us, and we notice, wait a second, the velocity is simply equal to the Hubble constant times the distances cancel out, and we get the inverse of the Hubble constant. And that gives us a time, a characteristic time. Now, if we use, let's say, the Planck mission's value for the Hubble constant, which is, say, 67.949 kilometers per second per megaparsec, then we get the Hubble time equal to 14.488 gigayears or billion years. Now that's interesting. But if let's say, oh wait, well, what about the alternate time? If from Cepheid variables, modern Cepheid variables give us 73.2 kilometers per second per megaparsec, and that gives us a different Hubble time of 13.358 billion years, not light years, years or gigayears. And that makes a big difference because the Cepheid variables show about 13.4, and cosmic microwave background shows about 14.5 billion year old for this characteristic Hubble time. That makes the Hubble constant important because that's almost a billion years of difference in the Hubble time. So, but the really important thing about the Hubble time is no matter what its value, it still has the same interpretation between the Cepheids and the cosmic microwave background measurements. If you go back in time, a time length of the Hubble time by the cosmological principle, every galaxy that existed was cramped that we see in every direction would be crammed on top of each other in some tiny volume of space. And so this is where Georges Lemaitre had the idea of the primeval fireball or primeval atom. And this was extremely controversial in the 1920s, but is no longer controversial today. So the Hubble time provides us a characteristic time of the universe. Taking a closer look at Georges Lemaitre's idea of the Big Bang, basically a Big Bang model of cosmology is one where everything starts out from some initially extremely dense state and then goes to a much, much lower density state due to this uniform and homogeneous expansion of spacetime. All right, so that's interesting. So how does this Hubble time that we just talked about compare to, say, old stars? Some of the oldest stars that are known are about 13.5 billion years old. And the oldest stars that we know are some of the halo stars in the Milky Way. And we know that they're old because their spectra are extremely metal poor. And metals for astronomers are any atomic element other than hydrogen and helium. That's all metals. Metals because they provide electrons when they're ionized. So as of this recording, the oldest known star has this really long name of 2 mass J 1808-2002-510-4378. Now, its metallicity is extraordinarily low. And metallicity is defined by the logarithmic ratio of how much iron there is compared to how much hydrogen there is in the spectrum. So there's some very prominent iron lines and very prominent hydrogen lines in stars. And so when you look at that, you say, oh, what's the prominence of these lines, these spectral lines in the spectroscopy of the stars? And the logarithmic difference is of less than -4, which means that this star has 1/10,000th of the metals of the sun. And I don't just mean like aluminum and magnesium and iron. It means everything. Anything heavier than helium has 1/10,000th of these atoms. So it's very, very, very metal poor. And Therefore, it's made up only of the primordial materials, and it's one of the oldest population 2 and possibly a population 3 star in the Milky Way. And the estimate is that it's 13.53 gigayears or billion years old. So in addition to those things, individual stars, Milky Way globular clusters have roughly ages around 12 billion years or 12 gigayears. What I've shown here is a picture I took with eye telescope. And this is Messier Object 13, a globular cluster, a beautiful one in the summer sky. And it's pictured here. It's about 11 and 11.6 gigayears old. Now, this one crazy one, the 2 mass, is an interesting one because there's 3 different populations of stars in the Milky Way. There's Pop 1, Pop 2, but there's the third Pop 3, which shouldn't exist in the Milky Way. Population 1 stars are very, very, very metal rich, and they are the youngest stars. Population 2 are older stars made from much older material when there was less and less processed material, less carbon, nitrogen, oxygen in the galaxy. Population 3 should be made only of hydrogen and helium and are the first stars. Now, this 2-mass star has extremely low metallicity, but it's in a binary system. So maybe it's a population 3 that is a binary system. And binaries, population 3 binaries, could be around today due to mass transfers when one of the stars in the binary aged, filled up during the asymptotic giant branch, expanded to a very large size, and dumped some material from one star onto the other, altering its future history. And so therefore, it could last longer because it lost some of its mass, and therefore it's around still today. And this is a new idea that came out about 2014 or so, is that some population 3 stars could be in the Milky Way if they're in binaries. I'll put a link to that 2-mass star and the population 3 binaries in the Milky Way in the description below. Okay, but for the Hubble time, this raw number really isn't the final word. The Hubble time could be wrong for a number of reasons, at least these 2. Gravity seems to work, and galaxies have mass, and that means there's an attractive force between galaxies that would slow down the expansion. And therefore, if that's the case, if it has slowed down, then the universe was expanding faster in the past, and therefore the universe would be younger than the inverse of h naught. All right, let's go through that again, just so we make it. So if it's slowing down the expansion, that means the universe is expanding faster in the past, which means that it's younger than h naught. H naught says it's a constant expansion, right? But that expansion rate could be changing, and there's reasons to think why it will be changing, and we will learn that it is changing throughout the rest of this course. Next, if there's a cosmological constant or something like it that's acting to speed up the universe's expansion, then that would lead the universe to being older than the inverse of h naught. And which one of these processes dominate? Is it the slowing down or the speeding up? Which of these dominates we're going to explore in later videos, and we'll construct toy universes and watch how their expansion histories change with time. And that's really interesting because that's really our study is how do we know how fast the universe is expanding or contracting? Not just this Hubble constant, but the actual form of the Hubble parameter, because when we looked at that originally with the triangle, there was no constant to that. That could change by any rate. The scale factor is just a function of time, and it can change with time. Likewise, we can also look at a characteristic distance size scale of the cosmos, and that's called the Hubble distance, which is the speed of light times the inverse of the Hubble constant. And for value of, say, the ESA Planck mission of 67.49 kilometers per second per megaparsec, that works out to be about 4.442 gigaparsecs, which is approximately 14.5 billion light years. So that's a typical size scale for a Hubble distance, meaning what's a Hubble distance? If you take everything that's within a radius of 14.5 billion light years, a Hubble time ago, everything was all in the same place. Everything that's inside that radius around us was on top of us at that time, a Hubble time ago. But let's just take a different thing. By comparison, the Cepheid studies, which is roughly 73.2 kilometers per second per megaparsec, then we get a Hubble distance of about 4.096 gigaparsecs, which is 13.36 gigalight years. And if you compare 13.36 to 14.49, Yeah, you're seeing that this Hubble tension is an incredibly important thing because with Cepheid variables, we're seeing a much smaller Hubble distance than we are with the cosmic microwave background. This Hubble tension is having some incredibly important results for really basic ideas about the characteristic size and age of the cosmos. Next, we can look at the result of the characteristic size scale of the universe due to an expanding, homogeneous, uniform expansion of the universe, is that helps us solve Olbers paradox. This is our resolution. Remember from the other time that we found that the characteristic fiducial size scale is about 10 to the 18th megaparsecs. If the universe is infinite and filled with stars, how far would we have to look in order to see a star? It's about 10 to the 18th megaparsecs. Oh, and incidentally, for those of you following at home, Olbers paradox is really only described for visible light, and it doesn't consider the cosmic microwave background. If we could see in microwaves, the universe would be uniformly bright at the temperature of 2.7 Kelvin, a uniform blackbody. But Olbers paradox is about starlight, not about the cosmic microwave background. It says, why isn't the sky as bright as the surface of the sun, given that an infinite universe that's infinitely old, an infinitely sized universe that's infinitely old? So 10 to the 18th is the characteristic value that you'd see for if you looked in any direction with this infinite eternal universe. Now, if we can only look out as far as 4,400 megaparsecs, that's really a lot smaller than 10 to the 18th megaparsecs. So the chance that we're going to see a star in our line of sight is simply this distance, this Hubble distance, divided by the characteristic size scale of the infinite universe. And the probability we're going to see that is about 4 times 10 to the minus 15th. That's a really tiny chance. So when you compare the surface brightness due to Olbers paradox, which would be the surface of the sun, and what we actually see from starlight in the universe would have to be 10 to the 12th times older, and all the stars would have to keep shining the entire time. So this is a really important thing. We know that stars don't live to be trillions of years. We do not think of the universe as that old. So the surface brightness is about 5 times 10 to the minus 4th watts per square meter per square arc second. But the sky brightness, due to starlight, or just light that is not the cosmic microwave background, is about 5 times 10 to the minus 17th watts per square meter per square arc second. It's much, 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 much dimmer. And therefore, Olbers paradox is solved by the finite age of the cosmos. And because the light has only had time to get to us from 4.4 gigaparsecs away. And there's the solution to Olbers paradox. Now, it wouldn't be a proper astronomy talk if we didn't talk about an argument. And the big argument against the Big Bang that started very early was the steady state model. In the 1940s, Hermann Bondi, Thomas Gold, and Fred Hoyle were the biggest promoters of a competing interpretation to the expansion of the universe. Einstein's static universe had fallen away because of the expansion that was discovered by Hubble and posited by Lemaitre. But the expansion could then have a different interpretation because a primeval fireball, a beginning of all time, was very disturbing to a lot of people, especially these three, and they created the steady state model. And they promoted it based off of the perfect cosmological principle that says not only are there no privileged places in space, why should there be privileged places in time, privileged moments in time? So the Copernican principle, which is no place is special in space, added to no time special in time, leads us to the steady state model. In fact, Fred Hoyle coined the term Big Bang in his BBC Science broadcasts, and there he is in front of his BBC microphone showing how to do science public outreach. And he was an incredible science speaker. So if you had a special moment in time, then you'd have a Big Bang. But in a steady state, since there's no special time, then what you measure for the Hubble constant would be constant for all time. And the cosmic density, therefore, because in the steady state, nothing changes in time, meaning the cosmic density, rho, would be constant in time, rho sub 0. That's also constant. So whatever the density that you measure today would have been the density a billion years ago, 15 billion years ago, 200 billion years ago, and 200 billion years in the future. This clashed hard with the Big Bang model, and both of these showed an expanding universe. So let's look at the mathematics behind it. By supposition, the steady state says that the expansion rate is constant and is proportional to the distance. We can then easily just state that the functional form of v is v equals h naught times r. The v then is by definition dr dt, the derivative of the distance with respect to time. This v is valid for all time. The Big Bang posits that this v can change in time because h naught is only the value of the Hubble parameter today. The Big Bang model states that h varies with time, thus making v having a potentially complicated form throughout cosmic time. But the steady state says h naught is a fixed constant for all time. This physics gives us the extremely simple differential equation that you see, dr dt equals h naught r, which can be easily integrated to give the distance. R is a function of cosmic time. R of t is proportional to the exponential of the Hubble constant times some cosmic time t. With a functional form of an exponential where v is equal to the derivative of the distance with respect to time, then we can then say, wait a second, if you take r, which is the distance, and run it backwards in time, meaning getting it smaller and smaller and smaller, we find that to get to 0, that we have to go back an infinite amount of time. So time has to go to negative infinity for r to go to 0. So therefore, in the steady state model, the steady state universe is infinitely old and has no beginning. Okay, so let's say it has no beginning. What is the current size of the universe? That's its volume. In order to get the volume of the current size of the universe, which has a characteristic length of the Hubble length, we of course take 4/3 pi r cubed, where it's a spherical volume centered on us. And if you cube that r, which is an exponential, you simply multiply the exponent by 3. So the volume is proportional to the exponential of 3 h naught t. Now, the density of the universe currently, the critical, is pretty close to the critical density, which is 5.9 times 10 to the minus 27th kilograms per cubic meter. If we keep that constant, matter would have to be continuously created inside that volume because that volume is expanding, right? So the matter that needs to be added in the steady state model, m dot steady state, is equal to, well, the volume change with respect to time. That's what the dot is, the change with respect to time, times the density. So the volume times the density, well, that's equal to, what's v dot? That's just the derivative of the exponential. And that is simply 3 times the Hubble constant times the volume times the density. So if we then say how much matter must be created per unit time, per unit volume, we get 3 times the Hubble constant times the density that we see today. And that's equivalent to about 1.74 times 10 to the minus 27th kilograms per cubic meter per gigayear or per billion years. So that's kind of a very tiny number. Can we make that relate to something? Sure. One proton is worth 1.67 times 10 to the minus 27th kilograms. That's the mass of one proton. And of course, there are 10 to the ninth cubic meters in 1 cubic kilometer, and there are 10 to the ninth years in a gigayear. That works out to be about 1 proton per cubic kilometer per year. That's about what's got to be created in the universe in order for the steady state model to work. You have to create matter, 1 proton for every cubic kilometer every year in the entire universe. Some proton just has to magically come out of nowhere. This is the core need of the steady state model. Long story short, the Big Bang did prevail in this argument. But how? Because the arguments are kind of the same. The people supporting the Big Bang said, creating matter continuously, that seems crazy. And then Hoyle and Bondi and Tom, they said, and Gold said, having everything created all at once, that's crazy. So it's kind of two really crazy ideas. And the universe is doing something crazy, whether it's creating matter continuously or having everything created all at once. Crazy meaning counterintuitive and not insane or wrong. Which one had to prevail? The discovery of the cosmic microwave background is the thing that really put the steady state theory to bed, simply because there's no way for a uniform cosmic microwave background to be created as part of a steady state theory. Also, just as important, is our galaxy evolution surveys, such as this image by the James Webb Space Telescope. This image is the JWST contribution to the GOODS South survey. GOODS stands for the Great Observatory's Origins Deep Survey. Most major telescopes or telescope arrays on the ground and in orbit have imaged this field. There's one in the northern sky and one in the southern. The goal is to do extraordinarily deep imagery of one patch of the sky to study the nature of galactic evolution. The field of view is really tiny, and they're therefore called pencil beam surveys. Since the galaxies imaged here are at great distances, because of light's finite speed, we're seeing them as they were a very long time ago. This survey has found that high redshift galaxies have a completely different appearance than local galaxies. This means there's been galactic evolution through time. In the steady state model, the farther out we go, we should see things exactly like the Milky Way, some things being formed, some mixture of things that are old and young galaxies. But the steady state basically says there should be no special time, so we should see a Milky Way if we look out 10 billion light years away. And we don't see Milky Ways, we don't see Andromedas, we see completely different kinds of galaxies. They are completely different in their appearance, their size, their magnitudes, how bright they are, what light they're emitting, everything. Therefore, the Big Bang idea prevailed due to the existence of the cosmic microwave background and the galaxy surveys, galaxy evolution surveys that have been shown. So we do know that it's expanding homogeneously and uniformly. Both the steady state and the Big Bang could solve that. But if it started in a dense, hot state and has been expanding ever since, then the cosmic microwave background is a direct prediction of the Big Bang, and not just some arbitrary hack add-on that the steady state model would have to do. The Big Bang predicts it, steady state doesn't predict it. Another really important element is the discovery of dark energy and dark matter. Both of these things will change the rate of expansion, the Hubble parameter, as a function of time. The steady state says it's always been the same, but knowing how the energy density of both dark matter and dark energy affect the rate of change shows that this rate of expansion could not be constant. So therefore, the Big Bang wins again. It's at this point when I give this public talk about the nature of the Big Bang, somebody says, well, what about the edge, past the edge of the universe? What's past the horizon, past the edge? Isn't there something, what's like on the edge of the universe? And that's an interesting metaphysical, conceptual question. But remember, there is no special place in the universe. Therefore, if we look at some distant galaxy that might be, say, 10 billion light years away, they would see the same thing, and they would ask the same questions. So that can be represented by this diagram of the nature of overlapping cosmic horizons. Let's say we're the yellow robot in the center. Our horizon would be the yellowish sort of ball that fades towards the edges. But each of the surrounding robots in each of their own galactic center, in their cosmic centers, each has their own center to their expansion. The red robot and the yellow robot are inside this, have a mutual universe, right? So the red robot's ball goes all the way around in that red ring. The purple robot has its red is purpley ring, and the blue robot has its blue ring. Each of these are separate cosmic horizons. Each of them sees the same Hubble expansion. Each of them would measure the same Hubble constant and have the same Hubble tension problem. But each of these observers don't necessarily see each other. The yellow observer sees all the three observers, but the red observer only sees the yellow, blue only sees the yellow, and purple only sees the yellow. Why? Because for the purple observer, the blue and red are simply too far away. They're outside the horizon. So the question that you could ask is, how many of these tiled horizons do we need to get the universe? And that answer is not at all well known. In fact, it isn't known. It could be an extraordinarily large thing. It could be a spherical geometry where the radius of curvature on this hyperspherical four-dimensional hypersphere is so large that we feel like our spherical distribution on the surface of that hypersphere is just a tiny fraction of that. But we cannot measure the curvature of the entire universe at all. So it is entirely possible that the universe itself is spatially infinite in extent, but it has a time at which it began. The best way to think about the Big Bang is that it happened in all space at one time, even though that space may very well have been infinite. That is the nature of the Big Bang. And every single observer has their own particular cosmic horizon. And that is a direct result of the cosmological principle and the homogeneous and isotropic expansion uniformly for all observers throughout the entire universe, which would be observers even outside of all of these horizons that we see in this diagram. All right, so what we've got here is a summary of the nature of redshift. The redshift itself is a measurable property that is observed in all galaxies. The farther away a galaxy is, the faster it's rushing away from us. The interpretation is there was a time in the past, what we call the Big Bang, where everything was in this hot, dense state and expanded from there. The expansion is isotropic, it's homogeneous, and it's uniform as per the cosmological principle. This is a fundamental expectation. The redshift is a prediction of the Big Bang. It's also a prediction of other expanding universes models, but the hot Big Bang has won out over all of those models. And right now, today, we believe, even though there is a Hubble tension, is to say exactly what the rate of expansion is, and maybe there's things we don't know about the Hubble expansion, or the Hubble-Lemaitre expansion, or the universe's expansion. There might be things we don't know about it, but there is no disagreement that the universe had a beginning and that it is expanding, and that expansion is currently accelerating. And that's the story of the redshift being proportional to distance. I just want to thank you for watching this and sticking with me. I also want to give a big thanks to my Patreon supporters. They've been fantastic through this thing to help me and give me some guidance and some support. And I'd like you to become a Patreon member too, if you'd like. So please check the link in the video. Also, if you enjoyed this video, please subscribe and hit that like button, share it on all those social media, and please come back because I'm going through the entire textbook of Barbara Ryden's Introduction to Cosmology. And so if you want to see what's going on in the future, please stay tuned, and we'll see you next time. Hello, this is Jason Kendall, and welcome to the next in my cosmology series. This is the fourth in chapter 2 of Barbara Ryden's cosmology textbook, Introduction to Cosmology. I'm going through the entire textbook, and if you are just tuning in for the first time, please see the link to the playlist in the description and go watch everything in advance first so that you can follow along in the correct order. That being said, let's begin with the different kinds of particles that exist in the universe. Okay, so let's begin by saying in cosmology, we want to look at all of the kinds of particles that matter cosmologically. And so this list is actually pretty short. We care about protons, we care about neutrons, we care about electrons, we care about neutrinos, we care about photons, and we care about dark matter. These are the dominant things that we care about in cosmology. And each of them, as you see in this little table, we have their symbols where the proton is a P and neutrons an N and electrons an E with a superscript minus. You have the neutrinos, which are the nu, the Greek letter nu, and they are three different flavors. There's the electron, nu, and tau. Photons are always given by gammas. And dark matter, we don't know what it is, so I'm just giving a crazy little icon there. Notice their rest energies and notice their charges. And so these are the typical particles that we're going to be talking about in this lecture. So when we do talk about particles, I'm ignoring a huge number of things that are in the standard model of elementary particle physics. Notice there are 17 different fundamental particles. There's 6 quarks, there's 6 leptons, there are 4 boson force carriers, and 1 scalar boson, the Higgs boson. All of these things are important for the standard model. However, many of them don't really matter to us in a certain regard. And I'm talking specifically about the quarks here, but all the rest of them do matter in other regards, as we'll talk about shortly. But these are our fundamental objects, and they're grouped into 2 different types of groups. One's the fermions and one's the bosons. Let's look more carefully at all these 17 particles in elementary particle physics. So we have 3 basic kinds of groups. There's fermions, hadrons, and bosons. Now, fermions have spin 1/2. It's one of their quantum numbers is a spin for all of these. And fermions all have 1/2 spin. Bosons all have single integer spin, or spin 1. Now, fermions can be broken into 2 different groups, leptons and baryons. And leptons are like the electrons and the neutrinos, and baryons are combinations or bundles of 3 quarks. Say 2 charms and a strange, or an antibottom, a bottom, and a top, or whatever, or 2 ups and a down. Those would be baryons. The other type of hadrons, which are quark bundles, are mesons, which would be a quark and its antiquark particularly. But all of the charges in a hadron must add up to 0 or 1. They have to be integers. We can't have anything in nature that is a non-integer, charge. So you notice how the charges on quarks are in units of 1/3. Either they're up at plus 2/3 or minus 1/3. So you can add them together, like a top and an antitop makes a meson, and a top and a pair of bottoms makes a baryon. So those are our types of things. Now, leptons are fundamental particles and quarks are fundamental particles. In fact, all of these are fundamental particles, meaning none of them can be broken down into smaller and smaller things. On the other side, mesons, because when there's 2 of them, they will have a unit spin because the quarks all have 1/2 spin. And if you have 2 of them, you get a single integer spin. Now that makes them bosons. And so bosons all have integer spin. Now there's certain ones that don't have mass. Notice that bosons that are force carriers are over on the right-hand side. The gluon is the force carrier for the strong nuclear force. The photon is the force carrier for the electromagnetic force. And the Z and W bosons are the force carriers for the weak nuclear force. The Higgs particle is the thing that creates the field of mass that we have. So, well, notice that I didn't include anything else. I mean, there is possibility, there's nothing excluding 4 quark bundles or 5 quarks or pentaquarks, but these pentaquark exotic baryons don't seem to exist in the wild, and neither do exotic tetraquark mesons. They are not barred from the standard model of particle physics, and they have been made and observed in particle colliders, but they don't exist in free space. They decay extraordinarily rapidly, and then they're done. But remember, all of these things, the quarks, must combine together to make integral charges, and those are the only kind of charges that are found in nature. So however you bunch the quarks together, that's how you get them. Now, quarks are so interesting. Let's talk a little bit more about them, about 2, 3, and 4, 5 quarks. So if they're in even numbers, they're called mesons, and if they're odd numbers, they'll be called baryons. If there are 2 or 3, they're normal meson or baryons, and anything greater than 3 will be exotics. And basically in quantum chromodynamics, this is how we actually know how quarks stay together. A quark's color can take one of 3 values of a color charge, red, green, and blue. And an antiquark can take one of the anti-colors, like anti-red, anti-green, or anti-blue. And they're represented by cyan and magenta and yellow in various and sundry diagrams. Gluons, which are the force carriers of the strong nuclear force, are mixtures of two colors, such as a red and an anti-green, which constitutes their color charge. So a baryon is composed of three quarks, in which each must have one of the colors red, green, and blue. Likewise, an antibaryon is composed of three antiquarks, one of which of each anti-red, anti-green, and anti-blue. And a meson is just simply made up of one quark and an antiquark, and therefore it has its color and its matching anticolor. All three of the colors, when mixed together, or any of these colors and its complement or negative, they're called colorless or white. And they have a net color charge of 0. And this is in a bound baryon, you'll find the color charge of the quarks as well as the two color charge of the gluon all add up to white. So let's say there's a green, red, and a blue. And then the gluon will say, I'm going to take my blue charge and leave a red. And so we now have an anti-red on the gluon and a blue. So the gluon now becomes blue and anti-red, shuffles over to the red charge, turns that red charge into a blue, leaving the red charge behind. And so the gluon will carry the source's color and the destination's anticolor as it traverses around. And so that's how quark gluon interactions go. Well, how does this relate to cosmology? Okay, so the only stable known baryons are the protons and the neutrons. And a proton is composed of two ups and a down quark, and a neutron is two downs and an up quark. Now, neutrons decay in about 15 minutes if they're free, and they won't fall apart if they're bound in a nucleus, say two neutrons and two protons in a helium nucleus. They won't decay. But if they're free and just roaming around, they're going to decay and break apart into a proton, an electron, and an antineutrino really quickly. But they're just also a little bit more massive than protons, and keeping things down, like a down quark, I guess, takes some weight, apparently. You'll notice that the mass of the neutron is about 939.6 megaelectron volts per c squared, where we usually say the c squared gives us a mass. So if we take the rest energy and divide it by the speed of light squared, we'll get a mass. But typically in particle physics, we quote things in megaelectron volts. That's typical for these things. Notice that the proton's rest mass is about 938.3 megaelectron volts per c squared. That's its rest mass. And it's a little bit less. Now, the neutron has 0 charge because of the sum of the quarks, and the proton has a plus charge because of the sum of the quark charges. So now the proton, though, is one of the most stable objects known. Its half-life is at least 1.7 times 10 to the 34th years, at least. And this is according to recent studies and recent attempts to actually find it, specifically by the Kamiokande experiment in Japan. Now, that's a long time. That's 10 to the 24th Hubble times, or 10 to the 24th times the current age of the universe. Protons are pretty stable. Now, what about charm and strange and top and bottom? Well, they don't make stable baryons. They do not make them. So these are the most stable and baryons known. Now we go over to the leptons, and specifically the electron. The electron is our special friend from all the leptons. It makes, with a proton and neutrons, makes up atomic nuclei. And they are tiny compared to the proton. They're approximately 1,840 times less massive. You'll see they're about a half a mega electron volt divided by c squared, of course. And they have a negative charge. And what's interesting is it looks like in the universe, there's one electron for every proton in existence. The universe appears to be electrically neutral, which is a fascinating thought. Why should that be? Why is the exact number almost identical? Well, it's a good question. And I'll have to get around to that in a future video, I'm sure, because that's just too fascinating to let go. Anyway, moving right along. Leptons are also part of the fermion group, and they're fundamental particles. There's also the muons and tau particles as well. And let's see what else we have. Next, we notice that 3/4 of all baryonic matter in the universe is hydrogen, with about 24% being helium, and there are various and sundry isotopes. But specifically, deuterium is very greatly depleted with respect to hydrogen, as is light helium. So it's pretty much just a proton with an electron spinning around it and a standard helium nucleus. That makes up almost all of the entire universe in terms of matter, in terms of baryonic matter. Basically, the universe is pretty basic. I mean, that's all there is to it. And so these are basically the particles of the universe: protons, neutrons, electrons, deuterium nuclei, light helium, a trace amount of tritium, which I didn't put in there, normal helium, and just a regular proton, a proton with an electron going around it, making up a hydrogen atom. This is it for the thing. Now, astronomers have an odd language, and this is their side note. Even though electrons are leptons, but since they come with 1-to-1 with protons, they're lumped into baryonic matter. Um, so when people say, oh, non-baryonic matter, they don't mean electrons. They do mean electrons for baryonic matter because they get dragged along for the electric neutrality. Now, they're 1,800 times less massive, so they barely contribute any serious mass to the universe, but they're not lumped in as non-baryonic matter for things that we'll talk about later. So if you're a particle physicist, please squirm now. I can't help you there. It's just the way it is. Electrons are lumped in with baryonic matter. Now let's look at another interesting side of the leptons. Neutrinos are another hugely populating particle throughout the cosmos. They're also leptons, and they basically don't interact with anything. They can pass through a parsec of lead without hitting a single nucleus. And we know about them principally through the nuclear reactions that are necessary to power the sun. And neutrinos can transform one into each other more easily in the presence of matter. Each flavor of neutrino, meaning electron neutrino, muon neutrino, or tau neutrino, is a quantum superposition of 3 different masses, which is kind of a weird way of saying things. That they can oscillate between each other is what's called the MSW effect. And go see my solar neutrino problem video to learn a lot more about this. So these things are really weird. And from the Planck cosmic microwave background results, we have an upper limit to their masses, because this is another thing. We don't know what their actual masses are. We know they exist, but we don't know what their masses are. We know the sum of their masses squared has to be less than 1/4 of an electron volt for all three, and that's from the Planck 2018 cosmic microwave background results from the anisotropy, from understanding the power spectrum of the anisotropy. Now, the Hubble tension issue can raise that value of 0.26 electron volts up to a total mass of about 68 electron volts. And that depends on the data set that's used and the methodology of the appropriately weighted combinations of the compatible data sets, such as ACT Data Release 4, the WMAP, Baryon Acoustic Sky Survey, and the SHOES collaboration. Now, this is because the Planck data is in tension with respect to more direct measurements of the Hubble parameter. So the Hubble parameter today is called the Hubble constant, and the cosmic microwave background shows it to be one thing, and these other things show it to be something different. And as a result, that changes the upper limit of the sum of the masses squared, which is really interesting. With all this, we certainly do know that neutrinos actually exist. We know about them as a result of the proton-proton chain in the center of the sun. Also, when a neutron decays into a proton and an electron, a predicted byproduct is an anti-electron neutrino, which has been observed in particle colliders. So, neutrinos have been posited to exist for a long time and have been observed coming from the sun and also from supernova 1987A, the first detection of neutrinos from a dying star. Now, this is where it gets kind of weird. We're used to thinking of particles as having mass, such as protons and neutrons. We know we can measure their masses in kilograms. And neutrinos were, when they were first originally considered, were thought to be massless. But now we know they have some finite mass. But the neutrino mass states do not correspond uniquely to the different flavors of the neutrinos. Neutrinos have 3 separate mass states, each of which are fractional probabilistic combinations of the three flavors. So as you can see from this diagram, we have we have the three colors for the three different flavors. We have the electron, muon neutrino, and the tau neutrino, and they're red, yellow, and blue. And you can see that their probability that it's one of those things gives it that mass. So the probability distribution shows what that mass number should be. And so there's three different mass states that correspond to three different combinations of the probabilities of whether or not it is that flavor. That's crazy to think about. So there's two possibilities for these groups, and the mass hierarchies, we'll call them the normal one on the left and the inverted hierarchy on the right. And so there's state 1 is the lowest in the normal, state 2 is above that, and it has a difference of the sum of the squares of two of the mass states. And then from 2 to 3 is the difference of a different pair of mass states. Now, the separation between these mass states depends on how they're measured. The smaller difference, delta m sol, comes from the measurement of the oscillation of solar neutrinos. This mass difference was responsible for the solar neutrino problem, where the total number of electron neutrinos was 1/3 of what was expected. The larger mass difference arises from the neutrino oscillations occurring due to cosmic rays striking the Earth's upper atmosphere. Such collisions create muons, which then decay rapidly to muon neutrinos and electron antineutrinos. The mass difference between delta M ATM reflects this interaction. Both of these differences are between squares of the mass eigenstates. We know the differences of the squares of each of the two mass states, but we don't know the individual masses for each neutrino. Instead, each mass state is made up of a combination of three flavors, as you can see illustrated. We don't know the absolute masses M1, M2, or M3 of any of these eigenstates. We just don't know. So delta M sub sol squared is equal to the state 2 squared minus state 1 squared, and that's approximately 7.5 times 10 to the minus fifth electron volts squared. Of course, you can divide by a c to the fourth here to get mass squared, but the energies in particle physics are usually stated in rest mass energies. Next, the atmospheric oscillations show that the mass differences between states 3 and 2, and that's approximately 2.5 times 10 to the minus 3 electron volts squared. The difference between the normal and inverted hierarchy will change those numbers a little bit. So let's take a guess and have fun with particle physics. Assume that the hierarchy is normal. If you prowl around the literature, it seems like there's a consensus that it's probably the normal hierarchy, meaning the left-hand diagram. So let's use that. Let's also then pretend that the mass state 1 is exactly 0. Then mass state 2 would be 8.7 times 10 to the minus 3 electron volts per c squared, and that quickly gives a mass state 3 of 0.507 electron volts. That's all nice and everything, but there is no requirement that the first mass state is 0, though. It's just a helpful exercise. Actually getting this mass is an active area of research with the Karlsruhe tritium neutrino experiment. This has the wonderful acronym of CATRIN. This experiment is trying to directly measure electron neutrino mass. In 2022, they reported a direct measurement of the electron antineutrino as just a little bit less than 0.8 electron volts per c squared. So neutrinos are not massless, but it's still possible that one of the mass states is massless. Neutrinos are really interesting. Cosmologically, we expect the universe to be filled with neutrinos, not just produced by nuclear fusion in stars or from the relativistic collisions in the interstellar medium, but principally we expect the vast majority to have been formed during the nucleosynthesis epoch of the Big Bang. Their number density should be extremely large, about a quarter of the number of cosmic microwave photons, which far exceed the total number of baryons in the universe. Okay, let's look at the next of our friends from the particle zoo that are cosmologically relevant, photons. Photons are very familiar to you. That's how you see things. And photons in our bucket that we're looking at, they have no mass. They are massless. They are spin 1 bosons, but they are electromagnetic radiation, and they have a particle-wave duality, and they can be thought of as either a wave or a stream of particles, depending on how you're measuring them. And both are measurable. So as a wave, it has a wavelength of lambda, which is equal to the speed of light divided by the frequency. And as a particle, photons have an energy and a momentum. But remember, even though they have momentum, they have no mass, where the energy of the photon, and we always use the subscript gamma for a photon, is equal to Planck's constant times the frequency, where h is equal to 2 pi times h bar, which is, of course, Planck's constant. But photons can come in a huge array of wavelengths spanning from gamma rays through visible light, through back up to X-rays, back down to UV, all the way down to infrared to radio, and the deepest, longest radio wavelengths. So they interact very readily with anything with a charge. They do through photoexcitation, which is exciting electrons in atoms up to higher levels, photoionization, where the electrons are kicked out of atoms, and photodissociation, where a high energy gamma ray can break apart a nucleus. And there's lots of names for these interactions. Free-free interactions, bound-free interactions, bound-bound, Bremsstrahlung, Compton scattering. All of these things are ways that photons interact with charged particles. In general, the photon can impart or take away energy from electrically charged particles, and they can easily be created by charged particles moving in the presence of other charged particles, or accelerating in the presence of other charged particles, or simply vibrating. The best way to think about a photon is that it is a packet of waves, a wave packet traveling from here to there along an electromagnetic field line that is infinite in extent. To learn more about this, go look at my entire long video on atoms and light. Let's look at a very important element of the nature of photons, and one of the most common things we're going to be talking about, and it'll be very important cosmologically, is the blackbody spectrum. So let's start with the idea that if you have an object that is dense and hot, then the electrons and protons and neutrons will interact, and they'll bounce off each other and vibrate against each other, and will create photons with an energy distribution that will match the thermal properties of the matter. Basically, all these particles in the object or system will be characterized by a single temperature T, and that will include the photons too. The chemical or nuclear makeup of the object does not matter at all. It's only the temperature when it's a dense object that's been all raised to the same thermal properties. The energy density of the photons in such an environment, let's look at their frequencies in a small, tiny range of, say, F up through F plus dF, with dF is a little tiny range. And this is given by the blackbody function that you see here. So epsilon as a function of frequency, and epsilon here is going to be in units of energy per unit volume per frequency band. So that's what we're going to be looking at. So you can see that there's an h bar, 8 pi h bar over c squared, and then you've got this function f cubed df, which is that little tiny thing. So we're looking at a differential equation. And at the bottom are the statistics for boson statistics, which is the exp hf over kt minus 1. That's the statistics, the thermal statistics for bosons. This is an interesting function, and in fact, there's a self-similar shape that I want to show you in that graph that we're looking at. That's that one little curve. That's the blackbody curve. Let's say now we redefine the variable x is equal to hf over kt, which is in that exponential. And we're going to reassign everything such that x is equal to hf over kt. And we get a new version of that formula. So you have e of x dx instead. And now you've got all the x's in the second part, which is x cubed dx over expx of minus 1. So that's our functional form of, say, x. But then the left-hand side is just a scale factor, which is 8 pi k cubed t cubed c cubed over c cubed h squared. And so that's a scale factor that would be applied to that curve. And so if you look closely, that curve that we see in the graph, that is simply the x cubed over x, but the exponential of x minus 1. And the t cubed is only it just will amplify everything on that curve the same. So all blackbody curves are the same. They all have the same shape. They're just changed by the scale factor of that c cubed h squared over 8 pi k cubed t cubed, with t is the temperature of the distribution. Otherwise, they're always the same. Now, the peak of the spectrum is that approximately the energy of the peak is HF peak, which is approximately 2.82 times kT, where kT is the characteristic thermal energy content of a particle in the gas. K is, of course, the Boltzmann constant, and T is the temperature. That's the energy of the peak of the Blackbody curve, and you can see that the hotter it is, the higher the energy. So first we have the energy density inside of a range. But what if we integrate the entire thing to get the energy density of the entire Blackbody photon field? So that's epsilon sub gamma, and that's equal to 4 over c times sigma, the Stefan-Boltzmann constant, times the temperature to the fourth power. That 4 over c arises from how the direction of diffusion and rate of movement of photons inside of a field are measured and integrated. 4 sigma over c is the radiation constant, which is that big squirrely nest of constants you see there. But notice the units. It's 7.56 times 10 to the minus 16th joules per cubic meter per Kelvin to the fourth. So this is an energy density. And the energy density depends on a constant times the temperature to the fourth power. So if you have twice as hot a gas of photons, it will have 16 times the energy density. So because the energy of a photon is h times the frequency, we can say what's the total number density of photons inside of the field. So we just take the energy density and divide it by the energy of one photon, and we have the number density of photons in a small frequency interval df. It's very similar to the previous expression, but there's an f squared instead of an f cubed. This will end up, after integration, to give a total number density of photons that depends on the temperature cubed. And if you work out the value of that beta constant, that constant beta, it's about 2 times 10 to the 7th photons per cubic meter per degree of temperature cubed. So there's a lot of photons in there. The hotter it is, the more photons you can have per cubic meter. That's an important thing we're going to be getting to later because we're going to be talking about the cosmic microwave background density as well. This also leads us to the mean energy, the average energy, not the peak energy, but the average energy, which is about 2.7 times kT, which is the typical energy for at that temperature. Wow, that's a lot about black bodies. How can we put this to some use? Well, if they have a temperature of 310 Kelvin, which is roughly you, if you're not sick or anything, then the average energy that's coming off of you is about 7/100ths of an electron volt. And that leads to a wavelength of about 1.7 times 10 to the minus fifth meters, which is about 17,000 nanometers. So you radiate in the mid-infrared. You're an infrared radiator. And so then when somebody comes up to you and says, oh, you're warm, that's because you're radiating a lot of mid-infrared photons. Now compare that to the sun. The surface of the sun is 5,800 Kelvin. Now the average solar photospheric photon is about 1.3 electron volts, which has a wavelength of approximately 900 nanometers, and that's in the near infrared. Wait a second, we can see the sun. When we can't see infrared light, we see the sun with visible light. But the Blackbody distribution curve guarantees that a lot of photons are present right next to the peak. Visible light is between 400 and 700 nanometers, and the sun has a huge amount of output right between 400 and 700 nanometers. Visible light lets you see, and the peak wavelengths keep you warm on a summer's day. Now, cosmologically, we expect the universe to be suffused with huge numbers of photons, not just from stars, but from nucleosynthesis processes in the Big Bang at the start of the universe. So photons in a blackbody are going to be really important in this lecture series. Lastly, we come in our discussion to dark matter. So dark matter is a really interesting thing and a subset of all of the materials that we're going to be talking about. It's one of the greatest mysteries. There's really no mysteries about protons and electrons and neutrons. Except neutrinos have some mysteries with the masses. And there's really not a lot of mysteries with photons. But comparatively speaking to these others, dark matter is a complete mystery. And what is it? So there's two basic definitions, and astronomers traditionally have called it there's mass there, but it's simply too dim to see. And that's its original definition. The term dark matter came from German, which was dunkle Materie, which was coined by Fritz Zwicky in his studies about the nature of the Milky Way. Now, particle physics and astrophysics will say that dark matter is anything that has mass that doesn't interact with photons in any way. It doesn't scatter light, it doesn't emit light, it doesn't absorb light, it doesn't create photons or anything. So why do we think that dark matter exists in the first place? Well, first, the Milky Way shows in its galactic rotation curves that it's not Keplerian motion in the outer areas. The rotation curves for almost every single spiral galaxy, in fact, all spiral galaxies, don't drop off the way they should if the center of the galaxy was where all the mass was concentrated. They have flat rotation curves out to their however far they can see, which means there's more mass there than is expected. So basically, they're rotating too fast at the outer reaches for the material that is visible to light. Next, massive elliptical galaxies have velocity dispersions of their stars that are too fast for the galaxy to stay confined. And next, similarly, galaxy cluster dynamics shows that individual galaxies inside of big clusters of galaxies tend to be moving too fast for the galaxy cluster to stay gravitationally bound. Gravitational lensing of background galaxies by foreground galaxy clusters also shows this because the only way to map the appearance of the background galaxies is to posit additional mass due to dark matter that exists inside of the galaxy cluster. Also, cosmic microwave anisotropies require that about 5/6 of the matter energy density be cold dark matter. That is, well, it's some sort of dark matter that behaves like matter, but is not the type of thing that's made up of protons and neutrons and so forth. Also, structure formation in the early universe. In the early universe, it was radiation dominated. And that would mean that the normal matter would interact with that light and be carried along by the photons that are incredibly intense. But since dark matter doesn't do light, it therefore can make clumps because mass works, right? Gravity works on mass. So it can make clumps, and then that would be the seeds of later galaxy clusters and structure that would be formed into superclusters of galaxies and so forth. Without this dark matter, there would be no clumping, and galaxy structure formation would happen far later than is seen. Now, technically, neutrinos do qualify as dark matter because they have mass, but the power spectrum of the cosmic microwave anisotropy measurements by the COBE, WMAP, and Planck require that hot dark matter, meaning dark matter that is moving close to the speed of light or relativistic, be in a really short supply. Basically, the existence of a lot of relativistic dark matter would also suppress structure formation in the early universe, making galaxy formation happen later. But recent JWST observations seem to be supporting an earlier and faster than expected galaxy formation, which means that you really do need dark matter in the early universe to create those seeds in order to make galaxy formation and galaxy structures. So what exactly is dark matter? Well, dark matter is kind of a weird thing. Let's just pretend for a while that it's like planets or burnt out stars or whatever, like huge amounts of gas and dust that are out there in the universe, made up of just protons and neutrons and other things. Maybe it's more hydrogen, maybe it's more helium, but that's baryonic dark matter. And there's a lot of lines of evidence that suggest that the majority of dark matter isn't baryonic. First, if there was gas or dust, then it would be, if there's enough of it to make the amount that needs to be seen, then that needs to be seen by the kinematics of things that we see, these velocity dispersions, rotation curves, and everything else we've seen, then it would be visible because it would come to the same temperature as the background stars. And this is similar to the Olbers Paradox argument. You have enough stuff in the way, it's going to absorb the light, and it'll get warmed up so you can see it. Next, Big Bang nucleosynthesis predicts the observed abundance of chemical elements. But if there's more baryons, then there will be also more helium and lithium and heavier elements synthesized during the Big Bang. So agreement with the observed abundances requires that baryonic matter only makes up about 4 or 5% of the universe's critical density, because we do think that the universe is a flat universe as a result of WMAP and COBE and the Planck probe, as well as many other things. So if that's the case, in large-scale structure observations and other observations indicate that the total matter density, including from this all, is about 30% of the critical density. So 30% of the critical density, which we think is actually the density of the universe, is actually in the form of some sort of cold dark matter. 5 parts dark matter, cold dark matter that's non-baryonic, and 1 part normal matter. Next, astronomical searches for gravitational microlensing in the Milky Way found only a small fraction of the dark matter maybe in the dark, compact, conventional things. And those things have this wonderful name of MACHOs, massive, compact, halo objects. These things, if we excluded, I mean, these searches have said, well, there's stuff out there, obviously, because, there will be black holes and there will be rogue planets, and those are interesting in their own regard. But there's not enough of them. And the excluded range of object masses goes from about half the Earth's mass up to about 30 solar masses, which would be some big, big, big black holes. And that covers almost everything that could contribute as machos. Finally, the WMAP and Planck probes indicate that, as I said, 5 out of 6 parts of the total matter is in a form that only gravitational effects. So that leaves us with non-baryonic dark matter. And there are 2 real main candidates for non-baryonic dark matter. One is hypothetical particles like axions, sterile neutrinos, WIMPs, weakly interacting massive particles, supersymmetric particles from the beyond the standard model of particle physics, atomic dark matter, or geons, which are black holes made of light. Kind of a weird thought. Or fundamentally, just simply primordial black holes. That's the other one. So basically, once a black hole ingests any kind of matter, baryonic or not, the distinction is lost. So you have no idea. So primordial black holes could be the fundamental non-baryonic dark matter with all the other stuff already floating around. Non-baryonic particles don't contribute to the formation of elements in the early universe. So they don't have any part of it. And so Big Bang nucleosynthesis is not affected by them. And so they would only find their presence through gravitational effects or weak lensing of background galaxies. But here's the thing. Dark matter, what it is still an incredibly wide open question. We know it exists, but we have no idea what it is. Okay, that rounds out kind of what we have for our particles in the universe, and we really kind of can break it back down with all that discussion to these 6 things. There's protons, there's neutrons, there's electrons, there's a bunch of neutrinos everywhere, there's a scad more photons than you can possibly imagine, and dark matter, a lot of it's there. We have no idea what it is. We don't know what it's made out of, but we know it's there. So these are our particles, and these are the typical particles that we will find in cosmology and that we're going to be using for the rest of the course. At this point, I'd like to say thanks to my Patreon supporters. They've been great for helping me along with all these kind of things, providing suggestions and so forth. And if you'd like to be a Patreon supporter too, please check the website out and subscribe. In any event, please like this video, subscribe to the channel, share it everywhere on social media. Let everybody know that there's cosmology happening over here on Kendall's channel. It'd be great to have you do that. And next time, we'll go through the final section of this chapter 2 for Ryden's textbook, which will be on the cosmic microwave background. See you soon. Hello, this is Jason Kendall, and welcome to the next of my Introductory Cosmology lectures. I'm continuing through Dr. Barbara Ryden's textbook, Introduction to Cosmology, second edition, and this is the last section of Chapter 2 on the fundamental observations, the cosmic microwave background. If you're just tuning in for the first time, please go check out the playlist in the description below, which will get you caught up in the correct order to watch this video series. Or you can go to my website, jasonkendallastronomer.com, and that'll also show you the correct order of these videos as well as the order of my complete Introductory Astronomy course, also on YouTube. So, without further ado, let's continue down this path of introductory cosmology and look at the cosmic microwave background. So to start with, what is light? Light is composed of photons. Photons are the carriers of the electromagnetic force. We can also think of them as packets of waves. Every photon has an indicative frequency and wavelength, and they also carry momentum, but always travel at the speed of light, which can be changed by the medium through which they're traveling. Light and photons exhibit a wave-particle duality. Sometimes you measure them for particle properties, and sometimes you measure them for wave properties. This is a big conundrum philosophically, of course, but doesn't affect our measurement of these properties. At any rate, they are produced easily by the movement and acceleration of charged particles. They're readily absorbed by electrons to make atomic transitions, and are readily emitted by electrons when they combine with a nucleus to make an atom. There also can be created by the annihilation of a particle and its antiparticle. Also, two high-energy photons can collide together in the presence of some charged particle to also create a particle and its antiparticle. So photons can be easily made and created and destroyed everywhere in the universe. Basically, if you shake a charged particle, you create an electromagnetic field, and the changes in that field are the photons. To learn more about light, please see my Introductory Astronomy lecture series about the interaction of light and matter. There's a link in the description below. Let's take a closer look at some of these properties of light. So when we're looking at the entire spectrum of light, there are lots of different frequency ranges and wavelength ranges. Notice that the frequencies can range from about 1,000 Hz up to 10 to the 23rd Hz. Likewise, the wavelengths can range from tens of kilometers down to 10 to the minus 15th meters, which are comparable to the sizes of atomic nuclei. This graph implicitly shows the energy of photons going from the low-energy radio photons all the way up to the high-energy gamma-ray photons. The part that we call visible or optical light only makes up a tiny sliver of all the possible wavelengths of light. For the cosmic microwave background, we're primarily concerned with the wavelengths between a few millimeters to a few centimeters. You can see that the CMB isn't as low frequency as, say, FM and AM radio bands, but there is a reason for all these space-based observatories that I'm going to be talking about for the cosmic microwave background. The atmosphere, and specifically water vapor, is a really good absorber of the CMB wavelength photons. And incidentally, this is why your microwave oven works, by the way. The oven's klystron emits white microwaves, which then basically boil the water in your food. It's heated by steam from the inside out. In any event, what we really care about are these photons that come from space, so putting orbital observatories to see this CMB background is extremely important. But there's a long and interesting history about the ground-based observations of the cosmic microwave background. In 1948, a number of important advances occurred in Big Bang cosmology. Ralph Alpher, upper left, was the graduate student at George Washington University under George Gamow, who has his head in his hand in that picture. Gamow had had some ideas about the origin of chemical elements in the Big Bang and assigned his graduate student to work on them, Ralph Alpher, and they proposed that the early universe could have created all the chemical elements. The subsequent paper, the so-called Alpher-Beta-Gamow paper, was the culmination of that work. Gamow included Hans Bethe, smiling in the lower right, in absentia to make the paper's title and authorship amusing and catchy. This deeply concerned and irritated Alpher, because Bethe was a great physicist who came up with the proton-proton chain, and Alpher rightly worried that he would be overshadowed. But published it was, and it became a famous seminal paper. Alpher completed his doctoral dissertation later that year in 1948, and in it he was the first to suggest that the early universe was likely dominated by radiation, and this opened the door for the detection of the cosmic microwave background. The Big Bang interpretation of this relic radiation was worked out in great physical detail by Alpher and Robert Hermann, the man in the mustache, in 1948 and 1949. Their work was followed by several peer-reviewed publications all the way up through 1953. However, Alpher and Hermann were not able to convince anyone in the early days of radio astronomy to go look for it. Using the best available values for the physical parameters that they knew, they consistently calculated the relic radiation should be observable at about 5 degrees Kelvin. This meant that 1948 could be regarded as the beginning of physical cosmology becoming part of mainstream physical science. Unfortunately, the notion that the pivotal year for the Big Bang cosmology was actually 1965 has been repeated by a lot of people, including myself and other videos and other contributors for a long time. So let me just recap the traditional story. In 1965, two researchers at Bell Labs, Arno Penzias and Robert Wilson, were using a horn antenna built for the NASA JPL ECHO project, which was designed to test microwave communications between California and New Jersey by bouncing the signal off a giant reflective orbiting balloon. ECHO 2 was this balloon. It was built by Bell Labs, launched in 1964 by NASA. As the balloon orbited, Bell Labs built ultra-sensitive radio receivers to pick up the faint signal from thousands of miles away. Penzias and Wilson were working on such detectors. Now, they needed to model and remove unwanted interference present in the signals. First, to get rid of thermal noise, they cooled the receiver with liquid helium down to 4 degrees Kelvin, or that's about minus 269 degrees Celsius. So, after they reduced their data, they found a low, steady, persistent, and quite intense background noise. This noise, was basically radiostatic, was spread evenly over the entire sky and was present at all times in day and night. And they noted that nearby New York City was a loud radio source, but that would be time variant and preferably bright to the east, so that wasn't the cause. And then they doggedly checked their equipment to remove pigeon nests and the usual white dielectric from the antenna horn, but the noise remained. This led them to be certain that this noise, which had a wavelength of about 7 centimeters, was not coming from the Earth, the Sun, or even the Milky Way. And this last thing, because the Milky Way is a plane in the sky with the center towards Sagittarius. If it were coming from the Milky Way, then there would be a preferential brightness on the plane of the Milky Way or towards Sagittarius in general. They concluded then that this noise had to originate outside our own galaxy, although they weren't aware of any radio source that could account for it. And this is where the trip to the older stacks of journal articles would have revealed Alpher and Hermann's work from the 1940s and 1950s. Instead, they contacted Robert Dick over at Princeton, just a few miles down the road. Dick was working with a team that was independently building their own radio antenna. See, in the 1960s, Dickey and Carl Brands were working on a theory of gravity, which led them to think about the early universe. They worked with Jim Peebles to rederive the prediction of the cosmic microwave background. This team also missed reading Alpher and Hermann's papers from the 40s and 50s. In any event, Dickey, David Todd Wilkinson, and Peter Roll began building a radiometer to search for the cosmic microwave background. When Penzias and Wilson contacted Dickey, he soon realized that their radiometer was no longer needed. The teams jointly published their findings in the Astrophysical Journal, with Penzias and Wilson describing the observation, and Dickey basically republishing Alpher and Hermann's earlier work, especially Alpher's PhD dissertation 20 years prior. That being said, the actual discovery by Penzias and Wilson gave them the Nobel Prize in 1978. For their part, Alpher and Hermann were awarded the Henry Draper Medal from the National Academy of Sciences in 1993, and the Magellanic Premium from the American Philosophical Society in 1975, and the Georges van der Linden Physics Prize from the Belgian Academy of Sciences. Further, in 2005, Alpher was awarded the National Medal of Science for his work in, of course, this nucleosynthesis and predicting that the universe's expansion left behind some sort of cosmic background radiation. So the story of Alpher's contribution is often lost or ignored in the story about the discovery of the cosmic microwave background by public speakers and teachers. This isn't due to some big conspiracy, but rather to the fact that it points to that even brilliant, capable, and ethical researchers and scholars can make errors that sting. To that end, according to Alpher's son Victor, Penzias had met with Alpher because he wanted a correct first-hand account of Alpher's work on the CMB before accepting his Nobel Prize in 1978 so that he could assure that his remarks in Oslo would give credit where credit was due. Once the cosmic microwave background was discovered by Penzias and Wilson in 1965, it then became an incredibly important and very active area of research. The culmination of that research was the creation of the COBE satellite, the Cosmic Background Explorer NASA satellite. This NASA satellite was launched in 1989, November, and was the first space-based observatory that was dedicated to observing the cosmic microwave background. The COBE team announced its measurements in 1992, and that provided two key pieces of evidence supporting the Big Bang theory. The cosmic microwave background had a near-perfect blackbody spectrum, and it has very faint anisotropies. Now, specifically, the most interesting thing that comes into my history is this graph of the far infrared absolute spectrophotometer, which is the FIRAS instrument. The cosmic microwave background spectrum is a nearly perfect blackbody with a temperature of 2.725 Kelvin. And these error bars on this graph are made so large that they're 400 sigma error bars. The 1 sigma error bars are not possible to see. They're smaller than the width of the line of the model on this graph. So it just would look like, oh, here's the graph. There's no data. And I remember going to the American Astronomical Society conference in January of 1993, where this was presented in Phoenix. And that was a really great moment. The entire place was filled. It wasn't their first place they announced it, but it was the first time they announced it to the American Astronomical Society. And it was greeted with an enormous, enormous standing ovation, which was an amazing thing. COBE's principal investigators, George Smoot and John Mather, received the Nobel Prize in 2006 for the discovery and form of the anisotropy of the cosmic microwave background. And the COBE project turned cosmology into a precision science as a result of that. Following right on the heels of COBE in 2001, NASA launched the follow-up mission, the Wilkinson Microwave Anisotropy Probe. COBE, having conclusively shown the near-perfect blackbody spectrum, meant that WMAP would then focus on the differences in temperature from this blackbody spectrum across the entire sky. The way to do that was to have a set of differential rather than absolute radiometers as detectors for the entire mission. This differential experiment is an interesting way to measure the cosmic microwave background. The WMAP measured the differences in temperature between two small areas of the sky across 5 critical wavelength bands, 13.6, 10, 7.5, 5, and 3.3 millimeters. A nice way to think about it is with an analogy to building something with a lot of wooden planks that all need to be the same length. You could take a tape measure and measure each one, or you could line up all the wooden planks next to each other to see how they all differ in length. Presumably, the lumberyard did a pretty good job in cutting down all of them to 2 meters, but you're going to check. Lining them all up, they should be all pretty close to the same length. That's why you chose the lumberyard, by the way. They're good at cutting stuff down to size. But you'll see tiny differences in length by comparing them all next to each other. And it is that variation that was being measured in the cosmic microwave background by the WMAP probe. Not the actual temperatures, but the variation in temperature from the average. So there were 2 fixed reflectors looking at patches in the sky in different directions. As the spacecraft rotated and in its orbit around the Lagrange 2 point, it was able to cover the entire sky many times in its 10 years from 2003 to 2013. The temperature difference between a black body in one direction compared to another for a given frequency band would be as good as 1 part in 100,000. So the temperature in one direction might be 2.7251 Kelvin in one direction, and in another direction, it might be 2.7249 Kelvin. Further, COBE could only see these tiny temperature differences on very large angular size scales, but WMAP could measure these differences on much smaller angular size scales. All right, so in this image, what we see on the left-hand side are images showing the temperature differences for each of the 5 observing bands with the lowest frequency at the top and the highest at the bottom. That is, photon energy goes from greater from top to bottom. The red spots are hotter than average and the blue spots are cooler than average. The bluest blue is 200 microkelvin cooler than average, and the reddest red is 200 microkelvin hotter than average. On the right-hand side are the models of the foreground emission that block our view of the cosmic microwave background, which must be subtracted. These maps give a feeling for the emission mechanisms that dominate as a function of the frequency and where they are in the sky. And again, they match the frequency band differential sky maps on the left. The colors on the right are different than those on the left. Red on the right is from galactic synchrotron emission, which is a non-thermal spectrum. Synchrotron radiation comes from relativistic electrons spiraling in the Milky Way's magnetic fields. So red, therefore, on the right-hand side, 5 images, tracks free electrons which can interact with the cosmic microwave background photons, change their energy and direction, and smear the spectrum and the angular resolution. Synchrotron radiation spectrum is not the same as a blackbody, so it can be very easily modeled. But that model strongly depends on the model of the Milky Way's magnetic field. The green colors on the right-hand side are from free emission. This indicates high-speed electrons passing by nuclei and either slowing down or speeding up. This is an acceleration of a charged particle, so it emits light, and such light is in the same wavelength bands as the cosmic microwave background. Notice how the green seems to be a lot lumpier? That's because this kind of emission will be in places where the electrons are ionized, such as star-forming regions or supernova remnants. So green therefore tracks hot gas. Finally, blue tracks the warm thermal dust. In the Milky Way, dust clouds would reside along star-forming regions and are composed of really tiny collections of atoms and molecules, not much bigger than a few microns in size, the same size as cigarette smoke. All 3 of these processes are low-energy electromagnetic interactions, all occurring in the Milky Way and all interfering with the observation of the cosmic microwave background. The central image is a combination of all the data on the left with the foreground emission modeling on the right subtracted away. At the 2014 American Astronomical Society conference, I chatted with David Spergel, one of the WMAP investigators, right after his plenary talk on the hunt for dark energy. He stated that one of the most important questions in all of cosmology is the accurate measurement and parameterization of the Milky Way's magnetic field and its dusty components. Knowing how to model and account for the foreground emission by the Milky Way has a direct impact on our understanding of the age, composition, and fate of the universe. The Wilkinson Microwave Anisotropy Probe ended its mission in 2013, providing an amazing 9-year map of the cosmic microwave background, and demonstrated that the universe is filled with 71% dark energy, 24% dark matter, and 5% normal matter. It gave huge support for the inflationary paradigm of the hot Big Bang, and all of these we'll talk about in upcoming lectures. Now, of course, COBE and WMAP are not the only things there. There are also balloon-based experiments. But the European Space Agency's Planck mission had even higher resolution than the previous 2. WMAP's resolution varied between about a degree for the highest frequencies and about a quarter of a degree for the lowest frequencies. The ESA Planck's mission had resolutions down to about 1/6 of a degree, so even tighter, as you can see here. So COBE, which started all, had a resolution of only about 10 degrees. That was good enough to get the overall cosmic microwave background spectrum, show the dipole in the sky, and show the blackbody temperature, and to prove that the hot Big Bang actually happened as cosmologists posited much, starting with Alpha in 1948. But the Planck mission went even further than that with its high-resolution imaging of the sky. The Planck mission, which is the European Space Agency satellite that you see here, was launched in May of 2009. It was named in honor of the German physicist Max Planck, who was a pioneer in quantum physics and in the theory of blackbody radiation, which makes total sense considering the cosmic microwave background is a perfect blackbody. Like WMAP, Planck was positioned near the second Lagrange point. Like WMAP, Planck constructed its full map from years of data of looking at the sky. And Planck had 2 instruments that covered radio emissions from 9 bands, unlike WMAP's smaller complement of 5. It measured the temperature fluctuations of the cosmic microwave background to 2 parts per million at an angular resolution of about a half a degree from the lowest frequency to about a 1/12 of a degree to the highest frequency. So these temperature fluctuations that you see in this picture also correspond to the density fluctuations from which the first galaxies formed. So the red is, of course, a very, very tiny, warmer area compared to the average, and blue is a cooler area compared to average. The high angular resolution and the ability to measure the cosmic microwave background's polarization allowed Planck to see what's called the Sunyaev-Zeldovich effect, which is a distortion of the cosmic microwave background caused by galaxy clusters. And it also observed gravitational lensing in the cosmic microwave background. However, more important than this really cool image of the full sky is the power spectrum of the temperature fluctuations that you see in this graph. The data in this graph are fitted by the line that has a number of input parameters. These parameters determine the shape of the line, and it is the optimization of the fit of the line to the data that tells us so much about the nature of the universe. These parameters are, first, the Hubble constant today, which is about 66.88 kilometers per second per megaparsec. Dark energy makes up about 68% of the energy density of the universe. Third, 27% of the universe is made up of dark matter. Fourth, 5% of the energy density of the universe is normal baryonic matter. Fifth, the age of the universe is 13.83 billion years. And the next one is that there are 3 neutrinos with a total mass sum of 0.23 electron volts, and this takes into account their maximum contribution to hot dark matter. And last, the total sum of all the energy densities of all the universe's contents is 1 to within 0.3%. This means the universe has a flat geometry on the largest scales. All of these we'll get into later in this course, but basically this shape, which is measured by WMAP and Planck and many other experiments, affirms the Big Bang, affirms the existence of dark energy, dark matter, the inflationary paradigm for the early universe, and shows that we live in a nearly perfectly flat cosmic geometry. Now that we've learned a little bit about the history of the cosmic microwave background and the observations that go to support the cosmic microwave background, let's summarize some of the most important elements about it. First, the spectrum that has been discovered in any direction is an almost perfect blackbody. Second, the temperature of that blackbody is exactly 2.72548 Kelvin, plus or minus 57 microkelvin. The temperature is measured to be nearly perfectly isotropic. There is a dipole anisotropy in the cosmic microwave background due to the net motion of all the added velocities of the Sun and the Earth experience embedded in the sky. That means the Sun traveling around the Milky Way falling towards the Virgo cluster, the motion of the Virgo cluster towards the Great Attractor, and potentially even the Great Attractor's motion throughout the cosmos. So we have a direction that we are going with respect to the cosmic microwave background. And finally, there are residual anisotropies in the temperature of the cosmic microwave background that are at most 1 part in 100,000 between any 2 points in the sky. These are the critical things in the cosmic microwave background. In my previous video, I talked a bit more about the nature of a black body radiation as per the particles in the cosmos, but let's do a quick review. So the wavelength of any given photon, lambda, is equal to the speed of light divided by its frequency. And photons do have energy and momentum, but of course no mass. Their energy of an individual photon is equal to Planck's constant times the frequency. And the black body energy density of photons get in a range of frequencies between a small little range, f, and up to some frequency f plus a little tiny frequency difference, df, is given by that equation you see on the top, which is the energy density of photons. And that's it's dependent upon a number of constants and the frequency cubed on the top of that expression divided by the energy, hf, of a photon compared to kT, the thermal temperature. So there's an exponential, and that exponential of that hf over kT is -1, indicates boson statistics. Now we can rearrange this by saying that x is equal to hf over kT, and we get that the x cubed over expx -1 indicates that there always, for every blackbody, they're always the same shape, and they're just simply changed by the scale factor of that T cubed. So if it's hotter temperature, it'll simply be this shape, but simply larger, basically by a factor of T cubed. Now, the total energy density across all wavelengths when you integrate the whole thing is 4 over c times sigma, which is the Stefan-Boltzmann constant, times T to the fourth. Or you can use A or alpha as the radiation constant there. And so the total energy density for photons goes like the temperature to the fourth power times a whole bunch of constants. The number density of photons is equal to, again, a constant times the temperature to the third power. And so that basically comes about by saying what is the energy, the top equation divided by the energy of one photon. So the peak of a blackbody spectrum is about 2.82 times kT, which is then given by the temperature. And the average photon energy is about 2.7 times kT, where kT is the thermal characteristic of the blackbody. We can now use this idea of the energy density and number density of photons to state a very interesting thing. Big Bang nucleosynthesis filled the universe with photons. Now, if we think of what the universe was like when it was only about 3 minutes old, it had cooled off enough to allow the fusion of hydrogen into helium. Prior to that, inside the first second, the photons that existed created a balance between photocreation and photoannihilation of quarks and their antiquarks, as well as leptons and their antileptons. Remember, this is what I was talking about at the beginning about how photons can be easily created and destroyed. This thermalized and fixed the blackbody spectrum of matter and light at a uniform temperature. For prior to the first microsecond, the temperature exceeded 10 to the 13th Kelvin. And all that existed were quark and antiquark and electron-antielectron interacting pairs and photons. And up till that little tiny first microsecond, inside the first microsecond, there was an equilibrium between particle and antiparticle pairs and photons. And that's what's represented by my little cartoons over here showing the reactions for quarks. After 10 to the minus 6 seconds, the temperature had cooled to 10 to the 13th Kelvin, which is, well, what is a billion? A billion is 10 to the ninth, so 10,000 billion Kelvin. The quark-antiquark equilibrium reactions stopped, somehow leaving a tiny imbalance with quarks outnumbering antiquarks, and I'll talk more about that in a future lecture. The destruction of the quark-antiquark pairs fixed then the total number of photons in the universe, where photons then vastly outnumbered all the remaining matter. Well, whatever matter remained. The remaining free quarks combined rapidly into hadrons, primarily protons and neutrons, and very quickly, there were no free quarks in the universe, and that means that matter that we would recognize today emerged at 1 microsecond. So the state of free protons and neutrons lasted about 3 minutes, during which sometimes some of the neutrons decayed into neutrinos and electrons and more protons, and the universe cooled, meaning the photons became rapidly less energetic, as did the matter. In the background, there was some sort of non-baryonic dark matter was being formed, but that didn't participate in the nucleosynthesis processes. At about 3 minutes, the universe had cooled down to a temperature at the center of the sun, giving the nuclear reaction chains that we see here. Basically, the proton-proton chain in its simplest form, since the CNO cycle wasn't possible. All the proton-proton chain steps created even more photons to add to the list created by the quark freeze-out that had just occurred. The final tally after all of this was done was that there was 1 helium atom for every 4 hydrogen atoms and 1 leftover deuterium for roughly every 100 normal hydrogen atoms. And for all of that, there were 10 to the 10th photons for every single particle. 10 billion photons in the cosmic microwave background for every hydrogen atom, helium atom, or deuterium atom. Now the expansion of the universe, since nucleosynthesis, the expansion of the universe has reduced the blackbody energy density. It has been reduced down to about 1/4 of a mega electron volt per cubic meter, which gives us a photon number density of about 4 times 10 to the 8th photons per cubic meter. The average energy of a current-day cosmic microwave background photon has lost its glory days. It can no longer photodissociate hadrons, and it now can't even excite most atomic transitions at an average wavelength of about 2 millimeters. However, they can excite molecular transitions, such as water vapor. So, cosmic microwave background photons rarely make it to the Earth's surface. In sum, the early universe's conditions created all of the cosmic microwave background photons. They all started off as gamma ray photons, the higher energy photons, and have been redshifted and expanded down into the radio. So now let's take a look at some of the regions of the blackbody spectrum of the cosmic microwave background. For the high energy tail of the spectrum, we can calculate what fraction of the photons have an energy greater than, say, some value. Here we're going to assume the energy of the photons that we're looking at is much greater than the average thermal energy kT. So the equation for the number density becomes a much simpler form, as you see. If we then ask how many photons of the cosmic microwave background are in the infrared, meaning with wavelengths shorter than a millimeter, it works out to be about 6% of the total cosmic microwave background is in the infrared. We could ask the percentage what are percentage are optical photons with a wavelength of less than 900 nanometers, and that works out to be something like 10 to the minus 2,518th. That's a number that is really so small that there are exactly 0 optical cosmic microwave background photons in the entire observable universe. Even the inflationary epoch wouldn't help here because that gives something like 10 to the 65 such Hubble spheres similar to our universe that we are assured of because of the inflationary epoch. So no matter what, all of the cosmic microwave background photons are infrared or longer, with the vast majority being centimeter length wavelengths. If you want to see how this derived, please join my YouTube channel and I'll be putting the solution there. Now let's see if we ask about the fraction that are longer than some wavelength, and we also get a pretty interesting result. UHF television channels, ultra-high frequency UHF, have a typical wavelength roughly around 10 centimeters, with the long wavelength approximation of the number density of photons in the blackbody spectrum. We get that there are approximately 250,000 UHF photons per cubic meter. It's not a lot. Since the antenna for UHF television tend to be pretty large and long, an estimate for a few meters of antenna length isn't bad. So we can just estimate that all those photons are captured per second. So how many photons on the TV that you see in this little picture from long ago were actually flashes from the Big Bang? Well, let's call a 1965 television a 100-watt emitter on that screen. These are visible light photons, and the old TVs had phosphor that was illuminated by scanning electron beam from the cathode in the back. So to keep things very easy, let's pretend that it's a 100-watt blackbody on that screen. It's not a great estimate, but it'll give a good idea. That'll give approximately 10 to the 20th photons being emitted by the television screen. So 1/4 of 10 to the 6th divided by 10 to the 20th gives us about 0.25 times 10 to the minus 14th photons, or roughly a millionth of a billionth of the photons on the television were cosmic microwave background photons. Not many, but they were there. Now, before I was talking about how the photons were created initially, but how did the spectrum of the cosmic microwave background arise? And where is that coming from that we see in the sky? So what we're looking at here is a video made by NASA Jet Propulsion Laboratories at Caltech in support of the ESA Planck mission. And what we're looking at is the state of the universe from nucleosynthesis until the universe was about 378,000 years old. So what you're seeing here during this time, the electrons were all ionized from the nuclei that were present in the cosmos. The nuclei are the red blobs, and they would be about 75% hydrogen, about 24% helium with trace amounts of other stuff. Now the green blobs are the electrons, and they're attracted to the nuclei by the electromagnetic force. But they can't combine with the nuclei to form atoms because the photons, here the bluish bolts, are so energetic that they keep the electrons in a state of high energy, much higher than the ionization energy of a hydrogen or helium atom. But the universe expanded and cooled until a redshift of about 1090, or a cosmic age of about 378,000 years old. At this time, the CMB photons went from something more like a cosmic optical or UV background to now an infrared background. This blackbody radiation at this newer, lower temperature was not enough to keep the electrons from binding with the nuclei to form atoms. Then, once the matter formed atoms, then the photons no longer significantly interacted with the matter, and this meant that the cosmic microwave background photons produced in the Big Bang could now stream freely on their way around the cosmos, hardly interacting anymore. Oddly, this time when the first atoms appeared in the universe is called the epoch of recombination. But they've never been combined before then, so it should be called the epoch of combination. Unfortunately, this is just yet another one of those astronomer things which started somewhere and stuck. The moment that the photons stopped interacting with the electrons came shortly after atoms started forming. This epoch is called decoupling, where the thermal properties of the photons and matter permanently diverged. That these two epochs are different but close in time should make some sense because if you're given a blackbody spectrum, the curve is a long high-energy tail. So even as atoms were forming due to the cooling of the photon field, the electrons still readily interacted with the photons. This meant that the electrons were just barely being captured by the atoms into higher atomic orbital levels. It would take a short while before the electrons would have a low enough energy to drop to the ground state of the atomic orbital shells. Those epochs are important because they create what we call a primordial light barrier. Prior to this time, light so readily scattered and interacted with electrons that it basically created a fog with an extremely short mean-free path for the photons before they interacted with anything. Once recombination started, the electron number density really dropped fast, or the free electron number density dropped fast. And at some point, the photon's mean free path equaled the Hubble length. Once that happened, the photons were now on their merry way across the universe in every direction, from every place. There is no single source for the cosmic microwave background. There's no place from which they originated. They were everywhere going everywhere in every direction. So once it cooled enough for them to make the atoms, then the cosmic microwave background sourced from everywhere. Now, the light that we see traveled to us straight for a Hubble time from every direction. Presumably, the cosmic microwave background photons that were formed where we are at are a Hubble length away from us, and some of them that were formed a half a Hubble length have bypassed us half a Hubble time ago. These photons are continuously streaming, and they are going to be streaming from everywhere in the universe. So now it's time to derive the temperature of the cosmic microwave background and how it changed with time. First, let's use the first law of thermodynamics. Well, what does this equation mean? So dq is a change of heat in the system. And whatever the system is that you wish to be talking about, whether it's a refrigerator or a cooler or an engine or the universe. dE is the change in the energy of the system, not the change in heat, the change in energy, which may be due to many sources, such as photons being created by quark-antiquark annihilation. The PDV is how much energy is mechanically put into the system by changing the system's volume under constant pressure. Next, we assume that the universe constitutes a closed system, meaning that no heat flows into or out of the universe. So what do we mean by heat? Heat is a measure of the change of temperature in a system. So when you place one system in contact with another system, then if that other one has a different temperature, meaning you place a hot something next to a cool something, like a hot iron skillet next to a hand, the hand will heat up and you will say, ow. So that will show that there's a temperature difference, which means there will be heat flow from the hot thing to the cool thing. And since the universe isn't, quote, touching another system, that would tell us that dq is equal to 0. So that's a kind of a funny way of talking about it. The universe is isolated and will be called an adiabatic system. Next, with that idea, then we can rearrange the first law and make the change that we're measuring for energy and volume and now pressure to be functions of time. So the dE dt is the rate of change of energy through time, and likewise dV dt is the change of volume through time. P of t is the pressure's explicit function of time. Well, remember, we call dq equals 0 to be adiabatic, meaning there's no exchange of heat with the surroundings, so we got rid of that and just simply rearranged. Now we need an expression for the energy. We can use that the energy density of a black body that we've been playing around with in the previous slides, and the volume V. That works out to be A, which is the radiation constant, times T to the fourth, or the temperature to the fourth, times the volume. So we really only care about the temperature here because A is the radiation constant. So we only care about that. Next, we can use the expression for the pressure due to blackbody radiation. That's 1/3 of the energy density. Normally, we think of pressure as a quantity directed against some surface. For a star, we visualize the outward pressure of the radiation against the surface that is opaque to the radiation and scatters it backward. And when the geometry is analyzed for all the incident photon angles upon a, quote, surface, it yields that 1/3 factor. So the radiation pressure is then 1/3 of the integrated photon energy density. So why do we use this for the universe? We're making a rather simplistic assumption that the surface of the universe is the size scale of the observable universe. Thus, it is a wall, even though it's not really a wall. It's just a sphere with the diameter of the Hubble length. But there's no boundary to the cosmos, so we can think of an infinite universe pushing against an infinite number of Hubble length size other observable universes intruding on ours. But no matter what, the radiation pressure due to an isotropic and homogeneous photon field will be the same everywhere. Therefore, every place in the universe is a surface which is being pressed on by the cosmic microwave background. Lastly, we know that a homogeneous, isotropic, expanding universe will have a volume that's proportional to the scale factor of the growth cubed. That scale factor, A, is not the same as the A in the energy density and pressure. Those A's are constants of the radiation field, composed of H bars and K's and C's. The scale factor, A, is purely a geometric function of time. Now we can take the expressions for the energy E, the pressure P, and the volume V and ram them into the equation above and take their needed derivatives with respect to time. When we do that, we get this really hairy-looking equation, right? Okay, remember that E was a function of temperature and volume. So the thing in the big parens is what we get when we apply the old 101 calculus product rule to a pair of functions of time. The right-hand side is much more compact with the substitution of the radiation pressure. On the second line, I've collected all the terms and canceled all the constants. And so we've ended with 1/t dt equals minus 1/3 over v dv dt. Okay, so now what I'm going to do then is plug v proportional to the scale factor cubed to get the next piece, which is kind of nerfy looking on the right. And so we've got at cubed and dat cubed, which is kind of ugly. But if we then take the derivative of that scale factor, we then get rid of that factor of 3, and we're left with a dA dt over a. And we don't get rid of the minus sign yet. Looking only at the first and last parts of this big equation string, and remember our college calculus, where 1 over something times the derivative of that something is the same as the derivative of that something's natural logarithm, it makes the easy-looking equation that we see here. We have to have 1 over t dt and 1 over a dA dt. Those are both natural logarithm derivatives. Integrating both sides and not worrying about constants of integration, we find that the temperature varies as the inverse of the scale factor. The larger the universe becomes, the lower the temperature is. Now, with the proper integration and using the standard that the scale factor of today is by definition 1, we get this simple formula that you see. Another one of my videos, I show you how the redshift is inversely proportional to the scale factor. At a redshift of 0, we're at a scale factor 1. At redshift 999, the universe was 1,000 times smaller, which leads us to the following interesting thing. We can calculate the temperature of the epoch of recombination using the Saha ionization equation. The Saha equation measures the state of ionization of the gas of particles, here protons and electrons, at a given temperature and pressure. I'll go into the Saha equation in later videos. But during the time of recombination, the universe had a temperature of just shy of 3,000 Kelvin. For the universe to be measured today to be 2.75 Kelvin, then the universe was 1,090 times smaller than it is today. The Hubble length at recombination, therefore, was only 13 million light years, which is much closer than the current distance to the Virgo cluster galaxy at 65 million light years. But then, of course, the Virgo cluster was closer back then too, due to the expansion being run backwards. But what's most interesting about the time of recombination is that the cosmic microwave background was a cosmic infrared background. The universe, at an age of 378,000 years old, 1,000 times smaller than it is today, the universe was as hot as the surface of Proxima Centauri, the closest star to the Sun. All right, that's a little bit about the cosmic microwave background and where it comes from, how we derive it, where we get this concept that there should be such a cosmic microwave background, and the fundamental observations that show that it really does exist and it is a perfect black body at a very low temperature, and we observe it in microwave frequencies. I'd like to thank you for watching and sticking with it. Please subscribe to the channel, and if you'd like to, please even join and become a member. If you do, you get to see videos released in advance, as well as featured member-only videos. You can also join my Patreon. Either one is fantastic. And we'll see you next time.